Okay, so our final talk of this session is going to be given by Laura Ratcliffe from Bristol, talking about simulating organic LEDs with large-scale DFT. So the floor is yours, Laura.
Yep. Okay, thank you very much, and thanks to the organizers for inviting me here. It's great to be back in Trieste. I haven't been here since my PhD, so it's been a while. So I'm going to be talking about simulating disorder in organic LEDs using large-scale DFT. So just a brief overview. So I'm going to start with a motivation of why OLEDs, why we're interested in disorder, why we need large-scale DFT for that. I'm then going to talk about how we do large-scale DFT. So by large here, I mean the thousands of atoms regime, and our particular flavor of doing that using a wavelet-based set approach. Then I'm going to focus a bit more time on how we go beyond the ground state, which is important for the type of OLEDs that I'm interested in, and then very briefly touch on an example of a particular type of OLED. So the motivation, so I mean, this doesn't really need explaining to this audience. I'm sure we're all familiar with the concept of trying to do computational materials discovery, the idea being that we want to somehow narrow down the search space for experimentalists who are looking for new materials which might work better for a particular application, whether that's kind of cheaper or more environmentally friendly or more efficient. Depends on the application in question. So I'm particularly interested in organic electronics. So these have a number of advantages, being that they're lightweight, low cost. They can also be flexible, so that leads to some interesting possibilities for devices, whether that's things like the curved TV here or the idea of kind of foldable and bendy screens. But one of the challenges for organic electronics is that we need to do kind of, if we want to do this workflow, of course we need to balance kind of two things. One, the cost of our calculations. If we want to screen a very large number of potential molecules, then we need our calculations to be cheap enough to do that. But we also need to balance that with the accuracy. Of course, if our calculations are not accurate enough, we're not going to be able to focus the search space in the way that we want to do so. So the particular challenge for OLEDs, so one of the properties that people are often interested in for charge transport is things like on-site energies and transfer integrals. And the usual approach of doing this is to start with a typical OLED structure, which is often very, very disordered, like this kind of snapshot you see here. And typically, we might extract pairs of molecules and calculate the transfer integrals for these pairs. One kind of limitation of this is that we are taking into account this disorder, but we're not including the effect of the environment on these parameters. And in some cases, the environment can have quite an important effect. So if we want to push more in the direction of accuracy, then we need to be able to do large systems. But at the same time, we need to be aware of this need to balance the computational cost. So I'm interested in a particular class of OLEDs, which have kind of been relatively recently discovered based on a process called thermally activated delayed fluorescence, or TADF. So the motivation for TADF is that most kind of OLED emitters in the current generation, or you can't see it because I've crossed it out, but are based on heavy metals like iridium or platinum. And this is not good from an environmental perspective, so we'd like to move towards something which could be purely organic. The advantage of TADF is that it can be purely organic, and it's basically based on this process of reverse intersystem crossing between the triplet and the singlet level. And if this singlet-triplet splitting is small enough, then this can be thermally activated. So we essentially get this delayed fluorescence process as well as the phosphorescence. So it's quite an efficient process. And as I said, it can be purely organic. So if we want to be able to find new TADF emitters, our key kind of parameter that we're interested in is this singlet-triplet splitting. But so the challenge here particularly is that the singlet-triplet splitting, both the singlet and the triplet, can be some combination of charge transfer and local excitations. So we need to really be able to handle both classes of excitations. And as with the charge transport parameters, the environment can also have a particular effect on the singlet-triplet splitting. So really, we'd like to be able to look at excitations in large systems. So this is an example of a TADF emitter, 2CZPN. Again, you can see a disordered structure, and we also have this internal molecular disorder that we have this rotation around these two angles, and we have all sorts of other distortions going on. So there's an opportunity to look at the ground state properties, but also particularly the excited state properties if we want to understand how the disorder and environment are important for TADF. So that's why I'm interested in large systems. So the question is how. So I work with a code called BigDFT, which is based on a wavelet basis set, which is a bit unusual in the DFT field. But in big DFT in particular, we use this type of wavelet basis set, which are called the least asymmetric Dilbershys of order 16. It's a bit of a mouthful, but basically they're these two squiggly functions. The red one is the scaling function, the blue one is the wavelet. And these have some nice properties in that they're orthogonal. They're localized in both real and Fourier space. And then more particularly, we can use them to define a multi-resolution approach. So in big DFT, that means we have this regular grid. We have some what we call fine grid points closer to the atoms where the wave function is strongly varying. And here we have both scaling functions and wavelets. And then further away, we have what we call the coarse grid where the wave function is less strongly varying, and we just have scaling functions. So this leads to quite an efficient approach, particularly if you have inhomogeneous systems. And we can also work with a range of boundary conditions, so from molecules through to fully periodic solids. In this particular work for the OLEDs, I'm mostly working with clusters in free boundary conditions. So it's an open source code in case you're interested in using it. But despite the nice properties of wavelets, it still is a cubic scaling code. So just like with plane waves, the computational cost increases as the cube of the number of atoms in the system. So this is still kind of a limitation that typically we can go up to maybe 1,000 atoms, maybe a few more. And we're mostly limited actually by the cubic scaling cost of the memory, but we'd really like to be able to go further. So how do we do that? So this is just a one-slide introduction to linear scaling big DFT. So the idea of linear scaling approaches is that they kind of want to exploit the principle of nearsightedness. So the idea behind nearsightedness is we're basically saying that the atoms or electrons don't really care about what's going on far away from them, so we should be able to somehow introduce some localization in our system. And in big DFT, we introduce localized what we call support functions. So this is an approach that's used in other linear scaling codes like OneTep and Conquest, for example. And these are basically numerical functions which are represented in wavelets. So this is an example of what they look like for this particular molecule. So we have S-like functions and P-like functions, also potentially D-like functions. But you can see that they're not strictly S orbitals. They are fully numerical. And so they don't kind of exactly retain the symmetry of S and P orbitals. So once we have these support functions, we can write our density matrix in terms of the support functions and what we call the density kernel. So these are our two main quantities that we use in linear scaling big DFT. And then the algorithm goes, basically, we start with some atomic orbital guess. We optimize our support function. So this means we minimize the energy of the system with respect to the numerical form of the support functions. So this basically enables us to start with to have some small basis. So for this system, we would literally have 4 basis functions on the carbon atom, so 1s and 3p orbitals, and then we optimize them to adapt to the system. So they essentially adapt some way to reflect their local chemical environment. And if you look closely, you can kind of see this is why we get slightly different S-like orbitals on carbon atoms with different environments. So these changes are actually quite subtle. So this 1D projection here, the dashed lines are showing our linear combination of atomic orbitals guess. The straight lines show the optimized orbitals. So the changes are quite subtle, but this is quite important for the accuracy. And so we do end up with a minimal basis, which is accurate and has an accuracy kind of similar to that of the underlying wavelets. And we also have a tunable parameter that if you increase the radius of these support functions, you get closer and closer to the cubic scaling result. So this enables us already to go to quite big systems, but if we're going to be doing lots of calculations, we want to reduce the cost as much as we possibly can. And so this led us to kind of think about what's the bottleneck. So as I showed, so we're optimizing the support functions and the kernel, but the support function optimization really takes quite a lot of our computational time. But we know that these support functions adapt to their local chemical environment. So if we would look at, for example, here a nanotube, you can see that along the tube in the same environment, the support functions look identical. Or in a kind of molecular system like this little water droplet, again, the support functions on one water molecule look very similar to those on another water molecule. So we have the idea that we should be able to somehow reuse this to reduce the cost of our calculations. So this led us to define what we call a molecular fragment approach. So the idea here is that we start with some representative fragment or molecule in our system. We optimize the support functions for that one molecule, which is very cheap because it's a small calculation. And then we replicate them and use them as a fixed basis for our larger system. So here it's a water droplet. In the applications I'm interested in, it's going to be a cluster of OLED molecules. So this enables us to get rid of this loop, which is going to lead to some quite big savings in computational cost. And there's just one more ingredient that we need. So these functions, as I mentioned, are numerical. They're based on a grid. So we need, first of all, to understand how we can do this rotor translation. And it turns out there's a well-established way of doing this. We just minimize this cost function, which basically gives us a rotation matrix between some template, so initial coordinates, and some final system coordinates. The nice thing about this cost function is that if it's a rigid transformation, then the cost function will be 0. If you have some distortions in the system, so if your water molecules are slightly fluctuating, this will be non-zero. So it also gives you some idea of the kind of distortions in your system. And then we just do a wavelet-based interpolation to actually get from one particular orientation to another. So when does this work? So there's two kind of caveats. So first of all, we need our fragments to be relatively weakly interacting. If you would have fragments which are very close together or linked by a covalent bond, then it doesn't make sense to use a basis set which was generated for isolated fragments. And then secondly, we also want the distortions to not be too big. So if you would have some molecule and you significantly change the bond length, this again might not be a good approximation. But for that, we have this cost function J, which tells us whether or not we're in that regime. When it does work, it reduces the computational cost by potentially up to an order of magnitude. So this is quite a significant saving, and it's worth doing for big systems. It's not relevant for this application, but we also do have a variation where we can use it for extended systems, which we call the pseudo-fragment approach. Just the last thing about fragments in big DFT. In the systems I'm interested in or talking about today, we have well-defined separable fragments, so these are single molecules. But in case you have something more complicated, like a biological system, so this is a lactase enzyme, we also have a couple of indicators which we've defined based on the density matrix, which allow us to determine whether or not part of the system could be treated as a separable fragment. And we also then have a fragment bond order, which means we can do things like draw maps between fragments. So this is quite useful for analysis if you have a system where it's maybe not so intuitive what the fragments should be. So just to summarize how we're doing large systems, so in big DFT, we have a range of methods from the cubic scaling to the linear scaling to the fragments, and then also some implicit solvent. You can see here the quite big difference in computational cost. That this is for clusters of CBP. This is an OLED molecule. You can see particularly the big difference between the linear scaling and the fragment approach, which is still linear scaling, but much cheaper. And just in case you're interested in how big we can go, we recently managed to treat the COVID spike protein, which has about 50,000 atoms on 16,000 cores in 6 hours for a single point calculation. So we don't quite need to go to the 50,000 atom limit for the OLEDs, but if we really need to, then we can. Okay, so now I want to talk about going beyond the ground state. So a few years back, we already implemented in big DFT constrained DFT, which for those of you who are not familiar with this approach, the idea is that we can find the lowest energy state satisfying some particular constraint on the density. In our case, we're interested in a charge constraint. So this is particularly useful for treating charge transfer excitations, and it's quite appealing because the cost is of a similar order of magnitude to ground state calculations, so it's relatively inexpensive. So the idea here is that we just add an extra term to our energy functional, so we have some Lagrange multiplier, we have our density kernel that we already introduced, we have some kind of weight matrix which defines where this charge should go, and then we have the charge that we want to transfer. So the aim with CDFT is that we should find the Lagrange multiplier, which gives us the required charge transfer, and then we just need to define where this charge is going to go. So in big DFT, we use a Loudon-like approach because this is very easily implemented with our support functions. And we also implement this within the fragment framework. We basically associate charge to a particular fragment. So CDFT and the fragments work well together. So we already applied this a few years back. This is the example I showed right at the beginning. So this is a more kind of traditional host-guest OLED structure. So this is iridium PPY3, so one of these iridium-based emitters in the CBP host. And we looked at different properties, so both the charge transfer integral, so this is based on a kind of fragment orbital approach, and then the on-site energies using constrained DFT. And here we were able to see both the kind of effect of the disorder in the transfer integrals, and then in the on-site energies, we could also see the effect of the environment. So this is kind of very nice to see that actually particularly the environment does make a big difference. We have quite a lot of dispersion due to the disorder. But this is charge transfer excitations only, and I mentioned that for TADF, we also want to do local excitations. So we can't really use traditional CDFT. We could use time-dependent DFT. This is the most common approach. But one of the problems with TDDFT is that if you're using a semi-local functional, there's a big problem with treating charge transfer excitations. So they're usually seriously underestimated. We can get around that by using hybrid functionals, particularly range-separated hybrid functionals, and going even further, tuned range-separated hybrid functionals work quite well for TADFs. But hybrid functionals with large systems are very expensive, even more so if you have to also tune for the particular system. So ideally, we'd like to be able to use a semi-local functional, not least because we don't have hybrid functionals available in linear scaling big DFT at the moment. We could also use another approach called delta SCF. So this is the advantage of being cheap, but you can have problems with local minima and also with spin contamination. So this kind of motivated us to define a new flavor of CDFT, which we call transition-based CDFT. And so the idea here, I'm not going to go into detail in the maths, but to give you a kind of flavor of what the constraint looks like, we basically impose a constraint between orbitals. So this could be, in this example, between the HOMO and the LUMO of a given fragment. So if it's a single molecule, you're basically imposing a constraint between the HOMO of that molecule and the LUMO of that molecule. As I'll show, it doesn't have to be the HOMO and LUMO, but just for example. So this is already compatible with the fragment approach, so we know we're going to be able to do large systems. In principle, it should be able to do both locally excited and charge transfer states. I'll show you how that works in practice. And we're also including self-consistency, so we're going beyond linear response. So the first kind of thing you need to do in CDFT is find this Lagrange multiplier. And it's not always trivial. It can be a bit expensive, take a few iterations to do. But the advantage if we have kind of a pure HOMO-LUMO transition is that we can't transfer more than one electron. So actually what we can do is just set the Lagrange multiplier arbitrarily large, and we never kind of surpass the correct number of electrons to transfer, or 2 if we're working with spin or not. So this means that we completely avoid the need to optimize the Lagrange multiplier, and so really the cost basically is the same as the ground state. Of course, we might not always want to do a HOMO-LUMO transition. More kind of importantly, we might not want to have a transition between just 2 orbitals. We might have some combination of transitions. There's also a question of how do you actually decide what transition to impose. So in our case, we're using TDDFT. This might seem a bit counterintuitive to do TDDFT and then constrain DFT afterwards, but the idea being that we could do TDDFT for a single molecule and then do the TCDFT calculation using that constraint for a much larger system. So we're fine with paying the price of one TDDFT calculation for a small system. So just looking at the A scene, so this is kind of the transition breakdown that you get from TDDFT. Predominantly HOMO-LUMO, but you have some small contributions from the HOMO -1 to LUMO +1, HOMO 1³ to +2. And so the way we do this with our approach is to do a separate calculation for each transition constraint, and then we sum up the density kernels using this transition breakdown weighting. So the cost does increase in that you need to do an extra calculation for each transition you want to impose, but you can still use just an arbitrary large VC. And you can see that kind of for a slightly larger contribution, you get a slightly bigger difference between the pure HOMO-LUMO and the mixed transition. By the time you get down to smaller contributions, this effect is quite small. So we wanted to test how this works for both local and charge transfer excitation. So we defined kind of a test set which has these A scenes, which are predominantly local, just using this kind of simple HOMO-LUMO spatial overlap as our metric for local versus charge transfer. And then we also looked at a handful of OLED molecules, which go from kind of mixed charge transfer local all the way down to kind of fully charged transfer. And these are kind of predominantly pure excitations, but the singlets do have some kind of small extra transition contributions. So first of all, the A scene. So we use as our benchmark data CCSDT values. So we find that if we compare the trends of the CCSDT with our TCDFT with PBE and TDDFT with PBE, so this is a local system, we expect TDDFT with PBE should work well. Our TCDFT gets very, very similar results to TDDFT. And so kind of the highlight here is that with a semi-local functional, we're doing as well as TDDFT, but cheaper, and we're doing better but delta SCF, but kind of similar cost. And not too much worse compared to hybrid functionals. So with local excitations, we're quite happy that it seems to work well. For the OLED, so these more charge transfer-like, we don't have any CCSD or other kind of reference values. These are quite large molecules. So we compared to range-separated TDDFT values, which are kind of tuned for the system. This is kind of our best reference we had. So here we find, just as an example, so this is the most charge transfer-like molecule. You can see this big failure of TDDFT with PBE, significantly underestimating. And we don't have that problem with TCDFT. So if we look at the errors, we can see that actually with PBE, we're outperforming both delta SCF and TDDFT, whilst being cheaper as well. So we're also kind of happy that we're doing pretty well with the charge transfer excitations. And if we just kind of want to look at this trend, if we compare TCDFT and TDDFT with PBE, we can see that for these local excitations, we get very similar results. So where TDDFT does well, so do we. And where TDDFT does badly, we get quite different results. So just to kind of summarize, we're pretty happy with the TCDFT approach, at least for the molecules we've tested so far. So we can do both the local excitations and the charge transfer excitations while you're still using a semi-local functional with a cost which is not too much higher than the ground state calculation. So this should enable us to go to the big systems that we're interested in. So just very briefly, I want to wrap up by showing an example of how we might use this in practice. So this is the 2CZPN molecule that I showed earlier, which is kind of a prototypical TADF emitter. So we started with a snapshot from classical molecular dynamics, this 500 molecules. If we want to look at, first of all, just the disorder in the gas phase, we used this cost function J that I mentioned earlier to kind of compare how similar the structures of each molecule are from this snapshot, and that enabled us to identify some representative molecules out of the snapshot to be able to calculate the parameters. So in the first instance, we've just looked at the ground state parameters, so both the valence X-ray photoelectron spectroscopy, which we compared with some experimental values, and we saw kind of some small influence of the disorder in the spectra. And then we also separately did the core XPS using a different wavelet-based code called MANNESS and the delta SCF approach, where we also kind of saw some small influence of the distortions. So this was interesting, but really we want to be able to look at the excited states. So 2CZPN was one of the molecules in our test set where things seem to work reasonably well. And so what we're working on at the moment is the idea of doing this workflow that, as I said, we start with TDDFT for a single molecule. We know in this case that both S1 and T1 are pure excitations. We extract some molecules and look at the TCDFT gas phase disorder. And then also we want to ultimately look at clusters and see how their excitation energies are affected by the environment. And so the idea here is that if we can bring all these things together, this is going to give us an improved description of the singlet-triplet splitting, and ultimately hopefully help us to try and identify and predict kind of more accurately which molecules could be good TADF emitters in which kind of environments. So just to summarize, so I've kind of talked about how we do DFT with wavelets for very large systems going to the kind of tens of thousands of atoms regime. So this is either using linear scaling big T or for systems where we have some repetition we can exploit, so we can use the fragment approach to reduce this cost further. I also talked about the TCDFT approach, which enables us to do locally excited and charge transfer states with a cost which is not too high a price to pay and which is compatible with our fragment approach. And then just briefly about this 2CZPN, how we've looked at the ground state disorder and we're trying to understand the excited state in the moment. So there's a few future directions. So this idea of looking at the environmental effect of the explicit excited states. We also, I haven't mentioned anything about forces. These results fall for vertical excitations. We want to look at adiabatic and also kind of look at the dynamics of the excited state. So that's something that's also a work in progress. Over the last few years, we've also worked a lot on PyBigDFT, our Python interface. So we've defined a lot of workflows to try and make these tools easier to use. So we have kind of published Jupyter notebooks, which do this kind of process of the TDDFT to the TCDFT approach. And then also working at the same time on a high throughput approach for TADF. And so just to finish with my acknowledgements, so Martina Stella, who's in the audience, she was a postdoc in my group, is now a fellow based here. Kritan Thapar, who's a PhD student in my group. Luigi Novisi and William Dawson, who worked on Big DFT. And then Natalie Fernando and Anna Raguz did the XPS measurements. So also just to acknowledge the funding and computer time. I do have a PhD position in my group in case you know anyone who's interested to work on this topic. And then I'll leave you with the references. And thank you for your attention.
Yeah,
Thank you very much for the very nice talk. Questions? Johannes.
Thanks. Very nice talk, Laura. I was wondering about when you do these calculations on the embedded system, so you have the molecule inside sort of many other molecules, and you use the semi-local DFT. Are you worried about? I mean, I assume that it doesn't fully capture the effect of screening from the other molecules. Is that something you're worried about, and thinking about how that could be included?
Yeah, that's a good question. I mean, so at the moment, we can't do hybrid functionals of large systems, so we have to hope it's not too important. But that is something that's on our radar for future work. So what we can do is do hybrid functionals in cubic big DFT, and it's actually easy to go from linear scaling to cubic. So one thing that we're kind of working on is doing a linear scaling calculation, then like a single iteration with hybrid functionals in the cubic scaling. So that's something to look at in the future, yeah.
Any other questions? Yeah, I was actually going to ask about that a little bit along these lines, but I was with the comparison for charge transfer excitations, if you're able to use hybrids, I guess if you're able to use a range-separated hybrid, presumably that would do better than, I think you were comparing with PBE. TDDFT, which would be a problem in those cases, but not necessarily for a range-separated hybrid. And with asymptotic exchange, I wondered if how that would compare with the method, this TCDFT method.
So the reference that we're using here was the range-separated.
It was,
hybrids.
okay.
Yep. So because that's kind of the best reference we
Right.
have really for these
Okay.
systems.
So it does compare very well with that.
Yep. So exactly, you can see, as you say, the TDDFT compares very badly, but the TCDFT is much more kind of reasonable and similar kind of accuracy to the PB0 comparisons with TDDFT. So. Yeah.
That went fast for me. Thanks.
Sorry. Yeah.
Other questions? I think we might be ready for coffee.
Yep.
So let's thank Laura again for a really very nice talk, and also speakers and coffee. See you at coffee. Yeah.
Thank you.
Okay, hello everyone. So I'm Gianmarco Rignanese from Université Catholique Louvain in Belgium, and I'm going to be chairing this session in which we have 3 speakers, invited speakers. But just before that, we'd like to have an announcement by Emilio Artacho.
Hello, good morning. This is a specific announcement for the members of the Scientific Advisory Board. We have a meeting at lunchtime, and we have a table in the cafeteria reserved for that. So please remember to go there, and it would be important to go swiftly. The agenda is quite packed, and the lunch break is not very long. And so a general announcement to everybody else, which is going to be something very un-British to say. If you see us, the members of the Scientific Board, around in the queue, we are going to try to jump the queue. We hope that you will allow us to do so. Otherwise, we don't have the time to discuss the things we have to discuss. Thank you very much.
Thank you, Emilio. Okay, so the first speaker of the session is Michele Simoncelli, and he's from the TCM group in Cambridge, and he's going to speak about the thermal conductivity of solid. The floor is yours.
Thank you. Okay, so let me start with Let me start with an outline of the talk. I will start discussing the Wigner transport equation and how it can be applied to describe thermal transport in materials ranging from crystals to glasses. I will show how this formulation allows to describe thermal transport beyond the semi-classical Peierls-Boltzmann limit, encompassing the emergence of particle-wave duality for heat. Then I will show how this formulation can be exploited to understand how to exploit structural disorder to vary the magnitude and trend of the thermal conductivity. The second part of the talk will focus on amorphous solids. In particular, I will describe the recently developed RWT computational protocol to comprehensively describe thermal transport in glasses from first principles. I will discuss how this allows to describe the effect of anharmonicity on the high temperature thermal conductivity of glasses. And then I will show some application of this protocol to silica glass, amorphous carbon, and amorphous alumina. Let me start from very general trends. The thermal conductivity of crystals display a decrease with temperature. You can see here experiments, scatter points, and the theory, the lines for 2 different crystals. You can see that the high temperature scaling is proportional to T-1, and this is explained correctly by the Peierls-Boltzmann theory for crystals, which was developed long ago. This equation describes thermal transport as a particle-like phenomenon. In particular, we have that the microscopic heat carriers drift and scatter similarly or in an analogous way to the particles of a classical gas. On the other hand, we have glasses which display a conductivity which is very low and display a very different trend. So we can see here a slightly increase with temperature. This different trend is related to a different heat transport mechanism, which was explained about 30 years ago by Allen and Feldman. And in particular, they show that heat transport in these materials is mediated by the coupling between quasi-degenerate vibrational eigenstates. And this theory holds in the regime in which disorder is the limiting factor for heat conduction. Actually, this picture is not complete because we have materials which are technically crystals, but they display a conductivity which is very low and deviates significantly from the T-1 scaling observed in simple crystals such as silicon or silicon dioxide. So here you can see that in these materials, for example, lanthanum zirconate, or cesium lead bromide, which are materials used in thermal barrier coatings or thermoelectrics, we have that Peierls-Boltzmann theory, the solid line, deviates significantly from the experiments. So in order to understand what is the main difference between these crystals such as silicon and silicon dioxide and lanthanum zirconate, for example, we have to look at the phonon dispersion relation. In silicon, we have that phonon dispersion is very simple. We have a small number of phonon bands, which are blue here, and anharmonic line widths, which are shaded red here, are very small. So we have interband spacings, which are much larger than the line widths. On the other hand, if we look at lanthanum zirconate at high temperature, we have a lot of phonon bands, and they are significantly overlapping due to large anharmonic line widths. So now I will show how to describe the thermal properties of these materials beyond the Piers-Boltzmann transport equation, using the Wigner formulation that we discussed a few years ago. The starting point of our work is the density matrix formulation. In particular, we start from the one-body density matrix. Here, Q second are wave vectors belonging to the Brillouin zone of the crystal. B and alpha are atomic and Cartesian indexes. At equilibrium, we have that the one-body density matrix is diagonal in the wave vector. This corresponds to the fact that at equilibrium, temperature is homogeneous, and we know that the density matrix of a system at equilibrium is diagonal in the basis of the eigenstates of the Hamiltonian. If we drive instead the system out of equilibrium, applying, for example, a temperature gradient, we have now that the one-body density matrix acquires off-diagonal elements in the wave vectors, and this corresponds to the fact that atoms vibrate more where temperature is hot, less where temperature is cold. And in order to describe this, we need basically wave packets, and so more than one single wave vector. The natural object to describe this out-of-equilibrium system is the Wigner distribution function, which is shown here. You can see the expression is quite complex, but the take-home message is that whenever you have a one-body density matrix carrying off-diagonal elements, you have a Wigner distribution which depends on space. And this is particularly convenient to describe this out-of-equilibrium regime, which we are able to track position, which is related to the temperature gradient driving transport, as well as the wave vector, which is a convenient label for the eigenstates of our system. Now, this object is a matrix, and in particular a matrix in the phonon band indexes, S and S prime, and one can show that the diagonal elements of this matrix are actually equivalent to the phonon population appearing in the standard Piers-Boltzmann equation, while the off-diagonal elements describe something more, and using the language of quantum optics, we call them coherences. Here you can see the transport equation for this Wigner distribution function. You can see that you have a commutator reminiscent of a density matrix evolution, and an anticommutator which is generalizing the term, the drift term appearing in the Piers-Boltzmann equation. This equation is useful because it allows us to compute the heat flux and therefore the thermal conductivity. The final result is quite complex, but it has a very simple interpretation. We have that the conductivity is the sum of two terms. The first term, in green here, is exactly the same that you obtain solving the standard Piers-Boltzmann equation and describe the particle-like or intra-band propagation of vibrational wave packets. The additional term, which we call coherence conductivity, becomes relevant whenever you have the interband spacing, which is smaller than the line width, so that you have significant overlap between different bands. And it is possible to show analytically that in the disordered harmonic limits, this coherence conductivity becomes equivalent to the Allen and Feldman conductivity for glasses. Then another work derived the same result using, or let's say derive a similar result relying on the Green-Kubo formulation. And later, also with Giovanni Caldarelli, Laran Benfatto, we show that actually the two approaches are totally equivalent. And very recently, Fiorentino and Baroni extended this demonstration of the equivalence also to the hydrodynamic regime. We can compute all the quantities entering in this thermal conductivity expression from first principles. Here you can see the results for lanthanum zirconate. So in green, you have the population or Piers-Boltzmann conductivity, which features the T-1 scaling. And in blue, you have this additional coherence conductivity, which has an opposite trend. And if you account for both of them, you correctly describe the total conductivity. At low temperature, we can see that the particle-like conductivity is dominant to the coherence conductivity, and this is because we have interband spacings larger than the line width, while at high temperature, we have interband spacing smaller than the line width, and the coherence conductivity is dominant. Now we want to understand more in detail what's happening, and so we resolved the particle-like conductivity and the coherence conductivity in terms of a density of particle-like and coherence conductivity. I will not enter into the details here, but it is possible to show analytically that the relative strength between particle-like and wave-like conductivity scales as the ratio between average interband spacing and line width. And this allows us to draw a regime diagram for thermal transport in which we have a frequency and line width here. So here in the orange region, we are in the overdamped regime in which line widths are larger than the frequency. We cannot say anything about this regime using the Wigner formulation because we are relying on the fact that phonons are well-defined quasi-particles. However, if we go here in the particle-like propagation regime, we have frequencies much larger than the line width, and this corresponds to the Peierls-Boltzmann or semi-classical regime, meaning that if we are in this region, we expect Peierls-Boltzmann theory to be accurate. And then, increasing the line width, we cross the average interband spacing, and we end up in the wave-like tunneling regime in which the Wigner function formalism is needed. Now, we can check computationally these analytical expectations, and the most natural way to do that is to basically recast this relationship in the space domain by just multiplying this by the group velocity. One can show that the ratio between average interband spacing and line width multiplied by the velocity gives you the ratio between the mean free path and the typical interatomic spacing. So we computed the mean free paths of our vibrations at 200 Kelvin, so at the low temperature where the population's conductivity is dominant compared to the wave-like conductivity. We can see here every circle is a phonon sampled in our thermal conductivity calculation. The size is proportional to the contribution of this vibrational mode to the thermal conductivity, and the color quantifies the origin of the contribution. So we use green for particle-like propagation, blue for wave-like tunneling, and red for something which is in between. We can see that the transition from the particle-like to the wave-like propagation is non-sharp, and it is centered around the interatomic spacing. However, here we are at low temperature in which particle-like conduction is dominant. If we increase temperature, an harmonicity kicks in, and it gives basically lower conductivity and shorter mean free paths. So now we have a lot of vibrations which are below the interatomic spacing, and we can see that all these vibrations are contributing to transport in a wave-like manner. Now I will discuss how it is possible to exploit structural disorder to actually tune the scaling law of the thermal conductivity of solids. Here you can see alpha quartz and meteoritic tridymite, two materials which have the same chemical composition but different structural disorder. You can see primitive cell of quartz contains 9 atoms, meteoritic tridymite you have 72 atoms, and the phonon dispersion relation you can see are quite different. So the average energy level spacing of quartz is much larger than that of meteoritic tridymite. This material is interesting because it can be found actually in meteorites. Here you can see a picture of the Steinbach meteorite which fell on Earth 300 years ago, and our collaborators at Sorbonne University managed to retrieve a sample of this material and perform experiments on the vibrational and thermal properties of this material. So let me start from vibrational properties of alpha quartz, which is the a very well-known material. Here you can see the line width as a function of frequency for alpha quartz at different temperatures. And we can see that vibrations are never in the overdamped regime, which is in purple here. So we can use the Wigner formulation to describe it. And most importantly, the line width are always below the average energy level spacing, which is the line here. So we have that quartz is a simple crystal, and we can see a signature of this being a simple crystal also in the Raman spectrum, we have a small number of Raman active modes, and we can see that at different temperature, the number of peaks in the Raman spectrum is always the same. So vibrational eigenstates are always well separated. If we look at meteoritic 3D mites instead, we have that the line width distribution is similar to that of quartz, but we can see that it crosses the average energy level spacing, which is now smaller. And then, if we look at the Raman spectrum, we can see that if we go from low temperature to high temperature, the number of peaks actually decreases because we have a merging of the Raman peaks due to the fact that anharmonic line widths are increasing with temperature. Here, we computed the thermal conductivity of meteoritic 3D mite and of alpha quartz and compared them with the experiments. Experiments for quartz taken from the literature. These for 3D mites were performed by our collaborators in Paris, group of Etienne Ballan. And we can see that we have a good agreement between theory and experiments in both cases. Now, we can expect the origin of this mild decay of the conductivity of meteoritic 3D mite, significantly deviating from T-1. So here I show the population and the coherence conductivity. Dotted is population, dashed is coherence. And we can see that this mild decay emerges from having a significant role played by the coherence conductivity. So this shows that meteoritic 3D mite is a complex crystal in which coherence conductivity is larger than population conductivity at high temperature, while quartz is always a simple crystal. We can study different polymorphs, for example, alpha cristobalite, which has the same ring statistic of 3D mite. And again, we find that it is a simple crystal in which heat conduction is dominated by particle-like conduction mechanism. And finally, we can go to the fully disordered case, which is vitreous silica, and we obtain a conductivity which is again in good agreement with experiments in this temperature range, and displays a trend which is completely different from that of crystals. So to sum up, we have shown that in meteoritic 3D mite, we can achieve a scaling of the conductivity which is totally intermediate between the decreasing trend of quartz and the increasing trend of silica. Now, in the final part of this talk, I will focus on the calculation of the thermal conductivities of amorphous materials. In particular, how to compute the conductivity of glasses using atomistic models containing hundreds of atoms. So in order to understand what are the subtle aspects related to the computation of the conductivity of glasses using small models, we have to look at the line width distribution for these different polymorphs. We can see that, in general, structural disorder doesn't have a strong effect on the line width distribution, but what changes is the average energy level spacing. So in crystals, average energy level spacing is well defined, but if we look at glasses, actually we have that the average energy level spacing depends on the size of the atomistic model that we use to represent our structure, our glass. And there are some subtle aspects related to this. To be more precise, it is useful to start from the Wigner thermal conductivity expression. Here, I've denoted with F the distribution, which is a Lorentzian, that is basically determining the strength of the coupling between vibrational eigenstates having different energy. So within the anharmonic theory, this distribution is a Lorentzian, which has a finite full width at half maximum determined by the line width. And instead, if we go to the harmonic limit in which an harmonicity phases out, this reduces to a Dirac delta. Long ago, Allen and Feldman discussed how this Dirac delta must be broadened with a distribution having a full width at half maximum of the order of the average energy level spacing. To understand why this prescription, we have to analyze the energy levels of a finite size model of a glass. So we consider a finite size models containing n atoms, and then we compute its energy levels, which are schematically represented here by the horizontal lines. We have that the average energy level spacing is the ratio between the maximum frequency divided by the number of modes. And if we then look at what is the overlap between these different energy levels due to an harmonicity, we have that at high temperature, we have significant overlap between neighboring vibrational energy levels because anharmonic line widths are large. But if we reduce temperature, we have that the line width becomes smaller and we no longer have significant overlap. So using just the bare anharmonic theory on this finite size model would imply that there is no coupling between these neighboring vibrational energy level. This is actually a finite size effect because we can double the size of our model so that we double the number of vibrational energy levels, and so the average spacings becomes smaller, and now we would have still coupling between neighboring vibrational energy levels. So this reasoning shows that actually in the harmonic limit and in the infinite size or astronomically larger size limit, we would always have coupling between neighboring vibrational eigenstates. And therefore, using the Allen and Feldman theory, using a broadening of the order of the average energy level spacing, ensure that this property is respected. We have checked computationally what happens if we evaluate Allen-Feldman theory in finite size models using a calculation at the gamma point only, or using the Fourier interpolation to actually improve the accuracy with which we sample the vibrational properties. And here we can see that in the calculation done using the interpolation, we have a range of value for the broadening parameter in which the conductivity and broadening. So we refer to this as a convergence plateau for Allen-Feldman theory. Instead, if we look at the calculation at the gamma point only, we actually have that it is very difficult to achieve computational convergence. And these statements are strengthened by this additional test performed on a larger models containing 5,000 atoms. We did this calculation relying on the state-of-the-art machine learning potential discussed by Erhard and others in these MPJ computational materials. Here we can see that increasing the size of the model, we actually obtain a convergence plateau, also doing a calculation at the gamma point only. And the convergence plateau using the interpolation mesh is wider. So this test shows that actually we cannot consider anharmonicity when the line widths are smaller than the value at which the convergence plateau starts. So we have actually to regularize our anharmonic theory in order to make sure that we respect the physical property of always having coupling between neighboring vibrational eigenstates in the low temperature limit. How do we do this in practice? Here you can see a calculation, a Wigner anharmonic calculation, so using the Lorentzian, on models having different size, and using or not the Fourier interpolation mesh to extrapolate the bulk limit. So the blue line here is a calculation done at the gamma point using a small model. Orange, solid, is a gamma calculation for a large model containing 5,000 atoms. And then dash blue is the small model studied with the Fourier mesh to extrapolate the bulk limit. And dashed orange is the large model studied with the Fourier mesh for the bulk limit. We can see that in the high temperature regime, we have good agreement between all the calculations that are studying a system which has a size of 1,000 of atoms, either explicitly studying it with a very, very large reference cell, or extrapolating the bulk limit with the Fourier mesh. If we go at low temperature, we can see that we have a divergence of the thermal conductivity, which occurs at a decreasingly lower temperature as we increase the size of the model. And this is a finite size effect, reminiscent of the crystal-like divergence of the conductivity that we observe in crystals. And we can get rid of this in practice by employing a regularization based on the Voigt profile. So we replace the distribution appearing in the thermal conductivity expression with a Voigt profile, which is the convolution between a Gaussian and a Lorentzian. And we use the eta parameter for this Voigt distribution equal to the beginning of the convergence plateau showed in the previous slide. So this prescription ensures that when we are at very, very low temperature, we are computing the conductivity using the Dirac delta appearing in the Allen and Feldman expression. And as we go at higher and higher temperature, we are actually accounting for an harmonicity using the Lorentzian distribution. Here you can see that the black line is the regularized Wigner conductivity, and the red is the Allen-Feldman calculation. So anharmonic effects in vitro silica are very weak. And here you can see that we have good agreement between regularized Wigner conductivity and Wigner conductivity in the large model. So in order to understand why the effects of anharmonicity are very weak in vitreous silica, we again look at the Wigner conductivity expression, and we see that in the high temperature limit, the thermal conductivity is actually a Lorentzian weighted average of velocity operator elements. The weights in this average depends on the frequency difference between, of the difference in frequency between the eigenstates coupled. So increasing temperature, we have that the anharmonic line width increases, so velocity operator elements related to eigenstates with increasingly larger frequency difference becomes more and more important. So we look at the velocity operator as a function of the frequency difference and the frequency average. And we can see that in vitreous silica, this is almost constant with respect to the frequency difference. So basically, this explains why in vitreous silica we have weak effects of anharmonicity, and also it explains how anharmonicity can more generally affect the thermal conductivity of glasses. By looking at how the velocity operator behaves, we can understand what will be the effect of anharmonicity. If the velocity operator were increasing with frequency difference, anharmonicity would increase the thermal conductivity. On the other hand, if it was decreasing with the frequency difference, anharmonicity would have had decreased the conductivity. A quick comment on the application of this computational framework to other amorphous material. We have applied it to amorphous carbon at different densities, and again we managed to describe quite accurately the experimental measurements. We check carefully finite size effect also in these materials, and the capability of this regularization protocol to actually achieve computational convergence using small models. And the very final slide is about the application of this framework to amorphous alumina, which allowed us to study this material from first principle. And again, we managed to obtain a good agreement between theory and experiments, and also study how the amorphous alumina can be synthesized at different densities, and we studied how density affects the conductivity of amorphous alumina, finding that basically increasing density gives you an increase of the thermal conductivity curve. And so I come to the conclusion of my talk. We have shown that the Wigner formalism allows to account for particle-like and wave-like heat conduction mechanism and to describe materials with different degree of disorder. We have shown that vibrations which have a mean free path below the interatomic spacing actually contribute to transport due to their wave-like capability to interfere and tunnel. We have shown that structural disorder can be used to engineer the thermal conductivity of solids. And finally, we have shown that this Voigt regularization protocol allows to study glasses from first principles. Thank you very much, and I am open to questions.
Thank you, Michele. Questions?
Very interesting talk. I have a kind of a naive question, but just so I understand it. So if, I guess what you're saying is that in a disordered case, as you increase the number of atoms per unit cell, as you increase the number of modes, you know, even if they have a fairly small line width, because there's so many modes, they're going to start to overlap. In that case, you expect the coherence or the wave-like conductivity to dominate or increase substantially?
Yes.
Okay. So it's basically, so any kind of disordered system is, I kind of maybe missed the very beginning of your talk, but that's kind of a general expectation that this wave-like contribution would be very important for any disordered system where you have a lot of modes almost independent of temperature, because you'll have so many modes, so densely spaced that even a small line width would lead to overlap.
Yeah, indeed, that's correct. The point is like it depends on how strong the overlap is, because you have basically different ways of tuning the strength of this overlap. One is varying anharmonicity, so you vary basically your line width, which can be varied, for example, with temperature. And the other is varying structural disorder, because you can basically engineer more or less the number of modes by choosing the number of atoms in your primitive cell.
And I have one follow-up question. When these modes are overlapping, energetically, it seems like tunneling is possible, but I guess it also depends on the eigenvectors of the modes at some level. Maybe could you imagine having modes in a disordered system that are spatially distinct and not overlapping?
Yeah, so that's a good point, actually, because having overlap, I would say, is necessary but not sufficient condition to have a contribution. So you need overlap, and also you need non-zero velocity operator elements coupling them.
Okay, so that's kind of
so if you have a localized modes, for example, they would a localized mode would be a mode having a zero velocity operator element with all the other modes.
Right. Okay.
And that would never contribute to the conductivity.
Thank you.
Maybe one last quick question. Sorry.
So since these are disordered things, of course, one crucial thing is the disordered configuration. So there can be different kinds of configurations. So is there a way of doing any configuration averaging? I guess you did it for a single configuration. Of course, as you are increasing the size of your cell, you sample probably many configuration. But, I mean, how exactly you tackled it, or what's your comment on it?
Yes, so that's another important point. In practice, we checked this by doing calculation on different models having the same size. And we applied the same framework to, for example, 5 different models, all having a size 192 atoms. And we always found the variation in the conductivity curves always within 5%. The details are reported in the paper, which is...
Okay, in the interest of time, sorry, we thank Michele again for the nice talk. And we move to the next speaker, Cyrus Dreyer from Stony Brook University.
Yeah, sounds like it's working. So thanks for the introduction, and I'd also like to thank the organizers for the invitation to this really interesting conference. Before I start, I'd just like to acknowledge my collaborators in this work. So they are David Vanderbilt and Shang Ren from Rutgers University, Max Stengel from Barcelona, John Bonini from the Flatiron Institute Center for Computational Quantum Physics, and Sinisa Ko from University of California, Riverside. So I think we've seen a couple of talks so far about anharmonicity. So I'll be talking about non-adiabaticity. And so just as kind of a very brief reminder, I think we have a lot of experts in the audience. to the adiabatic approximation that we usually make when we do electronic structure calculation. So in an electronic structure calculation, we have nuclei and we have electrons, and we oftentimes separate these in our calculation based on the fact that, of course, nuclei are much heavier. We expect their dynamics to be slower, and so we make the Born-Oppenheimer approximation. And there's a variety of different ways of kind of saying what the Born-Oppenheimer approximation is and the physics that it results in. But basically, the idea is that if we think about any kind of nuclear displacements, for example, the phonon mode, we assume that they're slow. We assume electrons are in their instantaneous ground states with static displacements. And also that the nuclei, if we construct an effective Hamiltonian for the nuclei, they basically move in the potential energy surface of these electronic states. So what I'll be talking about are situations where the Born-Oppenheimer approximation breaks down, or by basically going beyond this adiabatic approximation, we get some interesting phenomenon or interesting physics. And the two examples that I'll give are based on my title in metals and in magnets. So first I'll talk about how in metals, there's a concept of a non-adiabatic Born effective charge that requires, again, going beyond this Born-Oppenheimer approximation. And then in magnets, how we also need to go beyond the adiabatic limit to accurately include time reversal symmetry breaking in the phonon sector. So both of these cases based on lattice dynamics beyond the non-adiabatic regime. So starting off with metals, so one of the nice things about giving a talk to an electronic structure audience is that Born effective charges, the main topic of this part of my talk, is something that I think is known to many of you, and there are many experts in the audience on these types of quantities. So it's a quantity that we use a lot in first principles calculations, DFPT, lattice dynamics, et cetera. So the Born effective charges are a tensor. There's a value for each of the sublattices in the crystal. And then there's some directional indices, I and j. And there's, again, a variety of ways of thinking about Born effective charges. You can think about them as, for example, if you apply an electric field in a given direction to an ionic material, then you'll get some forces on the ions. You can also write this in terms of polarizations that are induced by an atomic displacement, or equivalently moments of the charge density that are also induced by some ionic displacement. And so the Born effective charges, they have units of charge, but of course it's a tensor, and it's defined as a dynamical charge, so it's defined through these perturbations. So it's not a real static charge that exists in your material. But one of the interesting things is that there is another connection between the Born effective charge and some static charge, and that is that there's a charge neutrality condition for the Born effective charges. So this was shown rigorously in this seminal paper by Pick, Cohen, and Martin, that if you sum over the sublattices of a crystal, sum of the Born effective charges is equal to 0. And this comes from the acoustic sum rule, as well as the neutrality of real charge in your system. So the reason that we're interested in Born effective charges is that they show up in a bunch of phenomenon in materials, including ferroelectric polarization, just the calculation of phonon dispersions, electron-phonon scattering, dielectric screening, electromechanical coupling, etc. But one of the things about all of these phenomenon is that they're usually associated with insulating systems. And so the question is, what about in metals? So in metals, do we have a concept of Born effective charges? Are they zero, non-zero, etc.? And so if we go back to our definition of the Born effective charges, at first sight, it seems like it's not applicable to metals. So in metals, we would screen any electric fields that we would try to apply to our system. any static electric fields. The polarization, electrical polarization, is not well defined in a metal, and also any moments of perturbed charge density are also screened. So it appears that maybe the Born effective charges are not relevant in metallic systems. However, the caveat to those arguments those kind of naive arguments I gave on the last slide, is that the total screening will, of course, only occur if we give time for the electrons to screen any electric fields. And so if we go beyond the adiabatic approximation, what we find is that there is actually a well-defined notion of a Born effective charge in conducting systems. And so the approach that we take to define this quantity is basically to start with a fully non-adiabatic quantity similar that looks like a Born effective charge, and take the zero frequency limit of this quantity and see if we get something well defined. So this idea has been done in the past, especially in the group of Francesco Mauri. And the idea is basically we can define a response function that is frequency dependent, that basically contains this susceptibility, and the susceptibility is a current response to some atomic displacement. And the susceptibility is frequency dependent and in general depends on wave vector. And then if we take the wave vector goes to zero limit first, and then we take the frequency goes to zero limit of this quantity, that's what we define as our Born effective charge. And so the key question is this zero frequency limit of this response function something that is well defined, something that is that can in general be non-zero? And so one way that we can understand this limit is to look at a similar response function that may be more familiar to most people, and that is replacing this susceptibility, which is the current susceptibility. And this gives us exactly so this gives us exactly the optical conductivity. And one thing that we know from textbooks about the optical conductivity is that if we take the zero frequency limit of this Q goes to zero susceptibility, then we get a constant, which is the Drude weight. And so we have a constant divided by frequency, and so we get a divergence in the optical conductivity at low frequency. And this is the well-known Drude peak in the real part of the optical conductivity that we see again in textbooks. And so just as kind of a reminder, so the Drude weight, we can write it in a variety of ways. I just write here an expression from independent particles. But basically the physics is it gives the density of free electrons that are available for conduction in a material. And so it's kind of a defining aspect of a metal. A metal has a non-zero Drude, general non-zero Drude weight, and an insulator has zero. So we just showed that there's this divergence in the optical conductivity. So does that also occur in this other response function? And the answer is no, at least if we have time reversal symmetry. And the reason is because the current is a time reversal odd quantity. And so for the optical conductivity, we have two odd quantities, which give us an even quantity overall. Whereas the lattice, the atomic displacement is time reversal even. So we have an even and an odd quantity. It's odd overall. And then what that means is that because, again, in time reversal symmetric metals, we can't have a steady current that is in response to a static displacement, and therefore this susceptibility needs to go to zero as frequency goes to zero. So kind of in a hand-waving way, we can say that we should get a well-defined zero frequency limit for this quantity. We can actually go one step further in comparing the optical conductivity and this other quantity. in order to determine what happens to that sum rule that I mentioned before. So if we formally compare these two quantities, we see that the sublattice sum of this kind of Born effective charge, finite frequency Born effective charge, is related directly to the optical conductivity, and therefore, if we take the zero frequency limit of both sides of this equation, then we see that the sublattice sum of the Born effective charges is actually basically proportional to the Drude weight. And so that means that, of course, in all metals, the sublattice sum of the Born effective charges will not vanish. And of course, this reduces to the charge neutrality condition in insulators, where the Drude weight is equal to 0. So the physics of this sum rule are actually pretty simple. So the idea is that, again, if we have our crystal, and now we group the electrons into ions that are electrons that are tightly bound to the nuclei, and free electrons, and then the sublattice sum of the Born effective charge basically means that we're shifting the entire crystal. But if we shift it in a non-adiabatic way, we will leave behind some charge density. And this charge density that's left behind is exactly the free charge, which is given by the Drude weight. Okay, so I've kind of just made some kind of hand-waving formal arguments, but we can actually calculate these quantities. I won't go through the details of the calculation, but we use kind of modified density functional perturbation theory techniques, and again, in a very similar way that has been calculated before in the Maori group. Requires electric field perturbations, atomic displacement perturbations, and we have to be careful, of course, because we're treating metals. So these calculations were implemented in the ab-init code, and here I just flash some of the computational details. And specifically, we use Wannier interpolation because we need a lot of k-points to converge the various quantities that are necessary for these calculations. So I'll just show two examples. One is a simple metal, FCC aluminum. The other is a doped insulator. So we'll look at electron-doped cubic strontium titanate. So for FCC aluminum, here what I'm showing, in blue we have the Born effective charge, so it's clearly non-zero. In black here, if you just focus on the black curve, that is basically minus the Drude weight. And if we add those two quantities together, just focusing on the red curve, we get the sum rule satisfied to very high accuracy as long as we have enough k-points to converge the Drude weight and the Born effective charges. So the situation is similar for strontium titanate. So what we're doing here is kind of at least the thought experiment of doping strontium titanate across the whole conduction band manifold made up of the titanium T2G states. And here we have Born effective charges for the oxygens and for the titanium and the strontium. And we see that the Born effective charges change as we dope. On the left-hand side of this plot, these would just be the normal adiabatic Born effective charges. And if we sum up the Born effective charges over this whole range and we subtract the Drude weight, then again we get this sum rule to be satisfied. Okay, so that's what I wanted to say about metals and this non-adiabatic Born effective charges, so that we find they're well defined in metals, at least in certain cases where you have time reversal symmetry. The sublattice sum of these Born effective charges is the Drude weight, and we have this DFPT implementation for calculating these quantities. So now I'll switch gears a little bit. Again, you'll see the theme of non-adiabatic lattice dynamics cropping up, but now I'll be talking about magnetic systems, so systems with time reversal symmetry breaking. And in this case, I'll only be talking about insulators. So, okay, so the place that we kind of started when we were thinking about this situation is the place you usually start when you do a lattice dynamics calculation. You calculate the interatomic force constants. So roughly speaking, if you displace an atom, you calculate the forces on all the other atoms, construct the force constants, dynamical matrix, get the phonons, et cetera. So then the question is, what happens in a magnetic system? Well, if you turn on magnetism in your calculation, which I indicate by these little circles, then maybe you have magnetic moments on some of your atoms, your electronic structure, your density changes, and compared to the case where magnetism is turned off, you have different forces and you have different interatomic force constants. Now, if you reverse the magnetization, then reverse the direction of these little circles, then the energy won't change. So actually, you'll get the same interatomic force constants, and then your equations of motion that you get your phonons from will have time reversal symmetry, even though time reversal symmetry is broken in the electronic sector. And so basically the idea is that the interatomic force constant matrix is time reversal symmetry by construction. And the reason is basically because we usually construct it by calculating these static forces. So if you want to explicitly include the time reversal symmetry breaking in the phonon sector that's present in the electron sector, then there's a variety of ways to do this. So one way was originally developed or kind of originally written down by Mead and Truller in this seminal paper, where we have to include in our effective Hamiltonian for the nuclei not only the scalar potential that comes, roughly speaking, from the electronic energies at a given nuclear configuration, but we also have to include a vector potential. And this vector potential is basically a Berry potential, a Berry connection in real space. So here R is a displacement of atoms in real space. And if you start from this effective Hamiltonian and you calculate the equations of motion, then in your equations of motion, you not only get the interatomic force constants, but you get an extra term that depends on frequency. So it's kind of a velocity dependence of the force. And this extra term contains basically a Berry curvature in real space. So again, these R's are displacements of atoms in real space. And so we can solve this equation of motion. We can get phonon frequencies. And so we did this with the example of an insulating ferromagnet, chromium triiodide. It's a 2D layered material. This is actually the bulk calculations. And what we get is shown in this kind of complicated plot here. Basically, for some of the phonon modes, so these are just phonon modes that are labeled by their IREPs, we have large contributions to this G matrix, this Berry curvature. And in those cases where this contribution or these matrix elements are large, then we get large splittings of phonon modes. So here the left is just the interatomic force constants. The right is what we call this Mead-Truller approach. And what will happen is these twofold degenerate modes will split into modes that have well-defined angular momentum, so chiral phonon modes. So we can list the angular momentum here. And so we can also look at the physics of what is happening in this system. And so basically what we have is we have magnetic moments on chromium, but the strong spin-orbit coupling is on the iodine atoms. And so basically what is happening is if we have phonon displacements of iodine atoms, the displacement of the iodine atoms is changing the easy axis for the chromium spins, and so the spins are canting. And if we move in a closed loop, then the spins will sweep out some area, and that will give us this non-trivial Berry curvature. So this is the physics behind what we're seeing, but this physics is troubling in the way that we've done the calculation. So actually, in the way that we've done the calculation, we've started from the Born-Oppenheimer approximation, So we're still in the adiabatic regime, but we see that the important dynamics in the system are spin dynamics. And spin dynamics, as opposed to maybe kind of the naive view of electron dynamics, are not necessarily faster than the phonon dynamics. The spin dynamics depend on the magnon frequencies and the relevant magnons. So sorry, I forgot to mention, we're always looking at the zone center. The relevant magnons in chromium triiodide are lower in frequency or around the same frequency as the relevant phonon modes in chromium triiodide. So we can't assume that that the magnetic degrees of freedom are fast compared to the ionic degrees of freedom, and we need to really compute the spin and phonon dynamics on the same footing. And so we did this in chromium triiodide with a simple model. So in the interest of time, I won't go into too many of the details, but basically just treating the spins semi-classically and treating a single set of degenerate phonon modes coupled to phonon modes coupled to a single magnon, and taking this Hamiltonian and solving the equations of motion for these coupled phonon magnons. And basically what we see if we do this is that the splittings between these chiral modes are greatly reduced. So that's the SP spin phonon column compared to the Meade-Truller column. And the physics is basically that the spins can't move fast enough to keep up with the phonon atomic displacements, and so the spins are sweeping out a smaller area, and therefore we have a smaller Berry curvature. And also it depends very sensitively on the magnon frequency versus the phonon frequency. So we can get a large splitting if the two coincide, and we get some large hybridization. So yeah, so that's all I wanted to say about magnets. In general, conventional calculations don't explicitly have this time reversal symmetry breaking in the phonon sector. We can account for it with velocity-dependent forces, but in cases where the relevant dynamics are the spin dynamics, then we need to include phonons and spins on the same footing. And so if you're interested in magnets or magnetic and phonon properties, then just a shout out to a poster by another collaborator, Asier Zaballo, who's a student of Max Stengel. He has a poster on basically external magnetic fields affecting vibrational properties in materials. Okay, so that's all I wanted to say about non-adiabatic lattice dynamics in metals and magnets. So thanks for your attention, and I'll take any questions.
Iris, thank you for respecting the timing. Questions?
Just a curiosity. In your definition of the effective charges, there is this proportionality with the susceptibility, the response function. So your charges have a complex part, right?
So if we go to finite frequency, then they definitely have a complex part. Yes.
Physically, what is the meaning?
Yeah, that is a good question. So we haven't thought about the finite frequency version that has a complex part. Yeah, I would have to think about that some more. Yeah. It may. Yeah. I don't want to get myself in trouble.
Cyrus, thank you for informing us and teaching us about some of these really subtle things. I want to make a general comment that's for the audience, and it's embedded in what you said. We've fooled ourselves for many years, and a lot of textbooks are just plain wrong in defining things like polarization and effective charges. That what's really physical, what can be measured, is currents. And we've just make things hard for ourselves by defining polarization and acting like it's a static property that's well defined. You know, what's really measurable is changes in polarization, charges moving around. And so once you have that attitude, and then that leads to this modern theory of polarization that involves Berry phases, is that you should have thought of it as currents all along. And it's adiabatic currents and an insulator, and then it's all this interesting other stuff in metals. So thank you.
Agreed. Yeah, thanks for the comment.
So what happened to bad metals? Like, do you think that you can apply this to bad metals where the single particle theory might not work?
So everything I showed is single particle physics. So it's definitely an interesting question about generalizing the concept of Born effective charges to systems with interactions. Yeah, so I guess there is a frequency range in which all the physics to deal with Born effective charges is relevant. So in bad metals, where you would expect kind of the scattering time to be quite short, this may not apply, because what we'd expect is if we have scattering time that is the scattering is faster than kind of the phonon frequencies, then the scattering will serve to get us back into the adiabatic regime. So that's the comment about scattering, not about correlations or correlated systems. Yeah.
Okay, thank you. I'm wondering if there are effects of non-adiabaticity also on systems where one typically applies the standard way of calculating Born effective charges, say semiconductors, 3-5 semiconductors or so.
Yeah, so there definitely can be with very small gap semiconductors, and Francisco Mauri's group has worked a little bit on this. So if you have a very small gap semiconductor, in principle you still have a gap, you don't have a metal, but then of course you don't have this nice breakdown of or this nice dichotomy in terms of staying in the instantaneous ground state, because the phonon frequencies can be of order of the gap. Does that answer your question?
Yeah. No, I have a question. In the case that you consider with so the interaction with magnons and phonons, so in principle you use the approach of the Berry curvature, which is if one linearize the equation in terms of omega, can come from instead a self-energy, non-adiabatic self-energy, and this was the approach that we use, the alternative approach. Do you think that in that approach, so in principle, that approach contains all the response, even the response to magnons? Is this, you think that you can get the same result, so considering both magnons and phonons with this second approach, which is equivalent to yours in the case
so
if you linearize respect to omega?
If you
so the one we use in the paper on the trimer and paint.
So you're asking about this approach?
Yeah, if this approach is equivalent, if you consider the full self-energy, non-adiabatic self-energy, with spin orbit interaction.
Yeah,
is equivalent to this or not?
I think yeah. So there's a few simplifications that we have here. that I think still could be nailed down better. And so one of them is just we're treating the spins as semi-classical, and I think that could be a difference between having the full self-energy, and also the spin canting mechanism. So the kind of just the true magnon-phonon coupling is only one part of the response. So or one part of the Berry curvature. So you would also have a Berry curvature with fixed spin and phonon displacement, moving phonons in a closed path, and then a kind of combination of these. So those we've also calculated in this context, and they turn out to be fairly small, but they're still corrections. So yeah, I don't know if that answers your question, but I think that this is kind of a more simplified. Yeah, maybe we can discuss more.
Okay, thanks, Harris, again. And we can move to the next talk by Francesco Macheda from the Università La Sapienza di Roma.
Okay, so good morning, everybody, and thanks for the kind introduction. So I'm Francesco Macheda, and I'm a postdoctoral researcher at Istituto Italiano di Tecnologia, currently hosted at La Sapienza, Rome. I earned my PhD 2 years ago at King's College London under the supervision of Dr. Nicola Bonini, who, as anticipated yesterday by Francesco, sadly passed away a few months ago at a very young age. Therefore, the organizer gave me the possibility to take 5 minutes of our time in order to remember him. And especially in this event where a lot of his colleagues and friends are present, and in a session also where most of the things that we are saying were of interest of Nicola's research topic. In order to remember him, I will just show some of the works that I think are very well known in the community, and regards vibrational properties, the study of vibrational properties of systems. For example, Nicola and co-workers were the first ones to pioneer the study of acoustic phonon lifetimes and thermal transport in freestanding strain graphene. In particular, they showed that in the long wavelength limit, the acoustic phonons acquire a finite line-width, therefore making them ill-defined semi-classical, ill-defined quasi-particles for samples whose dimension is larger than 1 micrometer. And this is entirely due to the behavior, to the quadratic dispersion of out-of-plane flexural modes, which are typical of two-dimensional membranes. And this apparent paradox is solved by the introduction of a small amount of strain, which rectifies the dispersion of the phonons around the origin. Another work which I think is very well known in the community and is very interesting is the study, the first example of first principle study of phonon harmonicities in graphite and graphene, in which Nicola and co-workers computed the line width and the line shift of phonon as a function of temperature, completely ab-initio by computing the third and fourth order force constants. And as regards instead, for example, the vibrational properties coupled to the electronic ones, one work which I find really interesting is the one in which Nicola and co-workers studied the intrinsic electrical resistivity of graphene. And this was the first example of a fully ab-initio calculation of the resistivity in which they were able to reproduce the low temperature resistivity, both in value and temperature dependence of intrinsic graphene. Whereas at room temperature, there is quite an astonishing result, which is that the ab-initio calculation fails to reproduce the value of the resistivity of around 40%, and this is still an open problem in the ab-initio study of the graphene resistivity. And at last, I would like to remember also the work I did with him, which was mostly about electronic and magnetotransport phenomena in doped semiconductors. Basically, we applied for the first time ab-initio techniques to the solution of the Boltzmann equation in presence of magnetic field, and we were able to compute coefficients such as the Hall scattering factor, Seebeck coefficient, magneto-Seebeck coefficient, and magneto resistivity, all from first principles. And a few words shall be chosen, and it's difficult to choose the word in order to describe the loss that we all had. Therefore, I will just say that he was a great master and a very kind person. And I would gently ask you to hold 1 minute of silence in his honor while I show some of his personal pictures. Okay, so that was Nicola, and okay, so passing to the talk. So I will talk about effective charges, mostly in line with also already presented in the very nice talk before mine. And in particular, we talk about effective charges and their effect on electron-phonon interactions, phonon dispersions, and the infrared spectroscopy in doped semiconductors, metals, and hydrogen-based high-temperature superconductors. Naturally, all this work wouldn't have been possible without the help of many collaborators, among which especially I thank Guglielmo Marchese, Matteo Calandra, Thibaut Soyer, Paolo Baroni, and Francesco Mauri. And as already said in the talk before mine, effective charges are the basic ingredients which is needed in order to describe the coupling of the vibrational system to the electromagnetic radiation. In particular, therefore, every experiment which produces a disturbance of electromagnetic nature in a crystal has to deal with the detection of effective charges. So let me start from the experimental side this time, and let's consider two of the main experiments which are used especially to study cutting-edge materials which may be made of small samples in order to characterize their vibrational properties. And these two are the electron energy loss spectroscopy, the EELS, in which a beam of monochromatic electron impinges on the material, and through the loss function of the particle, one can reconstruct the excitation of the system. In particular, we are interested in the one in the infrared spectrum, and also the infrared absorption of synchrotronic light. So for EELS, as I said, the one is interested to represent in a plot as a function of the momentum, the energy loss of the particles. In particular, one can reconstruct from the loss of the heat as a function of a momentum transfer a heat map, which can be superimposed over, for example, the phonon dispersion of the material. If you are interested in the dispersion of a phonon like excitation, this could be done also, for example, for polaronic stuff and for polaronic physics, but for what you are interested in this talk, we will talk about mostly phonons. And I represent here for graphite and bulk HABN the experimental result of the reconstruction of the energy loss as a function of momentum. Below, there is we represent the theoretical calculation that can are done through the calculation of Stokes cross-section. And in particular, the thing that I wanted you to notice is that some part of the dispersion are hot and some part of the dispersion are cold, in the sense that the coupling of the electrons interaction to the phonons is governed by something which has some selection rules, and in particular, these quantities are, as I said before, the effective charges. Interestingly, this can also be seen in the infrared absorption. For example, here I report an experiment done on calcium aluminium silicide, which is a BCS superconductor of a critical temperature of about 4 Kelvin, in which we can see the reflectivity spectrum as a function of the frequency. In particular, we can notice that before the sharp drop due to the onset of the plasma frequency, we have a very high reflectivity, but which is not exactly 1. And therefore, it allows for the appearance of some additional peaks that have room to appear. And in particular, here, there was a detection of a peak at 200 centimeters to the -1, which may be used to probe the infrared vibrational spectrum of reflectivity, which is related to the presence of phonons. Of course, even here, the intensity of the peaks is related to effective charges that are present also in metals, as was presented in the talk, in the previous talk. Now, we would like to describe all of these experimental features and have a general theoretical framework in which we can describe the coupling of electromagnetic radiation to phonons. In order to do so, the object of desire for the theoretical description is usually the electric function. The electric function which relates the external potential to the total potential that is present in the crystal. We may make some idealizations and some approximation in which we treat the system as an infinite crystal and we disregard the retardation effects of light. So in particular, we consider the absence of magnetic fields. In such case, all the physics may be contained in the Fourier transform of the electric function, which depends on the wave vector Q and on the reciprocal lattice vector G and G prime. A useful factorization that can be used in order to study the response is the one in which we separate the electronic and the vibrational degrees of freedom of the system. Though this separation doesn't mean that the two parts are independent, and in particular the vibrational part is strongly tied to the electronic one. This separation comes from the many-body, from a many-body point of view, from the separation of the Coulomb kernel in an electronic and phononic contribution. We are mostly interested in this part because it's the one which experiment that looks at the vibration probes, and in particular, it can be shown that this part may be rewritten as a function of quantities that are called transverse effective charges, but we will call also them unscreened effective charges for reasons that I will show you later, and also as a function of the macroscopic inverse dielectric function of the electronic system. And beyond the definition of the transverse effective charges, we can also define the longitudinal effective charges, which includes also the effect of screening and are defined as the product of the transverse or a screened effective charges and the macroscopic dielectric screening of electrons, and they can be operatively defined as the induced density following a perturbation of the system, plus the perturbation itself, divided by the magnitude of the wave vector. The difference between longitudinal and transverse effective charges is basically the fact that is related to the presence of electronic screening. It can be shown that transverse effective charges may be expressed as a function of Born effective charges and dynamical quadruples, and so forth and so on, as far as one can go with the expansion. And the important thing to relate with experiments is that the Hills cross-section that I showed at the beginning are related to the longitudinal effective charges, whereas the infrared absorption is related to the transverse one. So we'll keep for now a static description for the first part of the talk, whereas we will move to a frequency dependent one for the second part. So, as also anticipated in the previous talk, what one is interested usually is to extend the definition of effective charges to the case of doped semiconductors and metals, because what I told up to now is more or less textbook physics rearranged in a different way. But the thing is that polarization seemingly is not well defined when free carriers are present, so we may ask if in the presence of free carriers, if that's where the electric tensor is strongly dependent on intraband terms and it's divergent on the Thomas Fermi scale, we can still define transverse effective charges. And we're also interested in understanding what happens to observables which are related to the presence of macroscopic charges in the system. So, in particular, we will study the effect of this expansion of the formalism on the longitudinal or screened effective charges through their effect on the electron phonon and phonon dispersion in doped semiconductors, whereas for the unscreened one, we will study this extension with the effects on the infrared reflectivity spectra. So let's start from the screened effective charges. Now, let's take cubic silicon carbide, which is elemental semiconductors, and let's dope it with a small quantity of dopants, in particular of holes in this case. And let's consider effective charges and their definition. So we can plot the screened effective charges as a function of the wave vector along a high symmetry line in the Brillouin zone. And we can plot it for the undoped case, represented by circles, and for the doped case, represented by squares. We can see that in the undoped case, the screened effective charges tends to a constant value, which is the same one that can be computed by standard codes such as quantum espresso at q equals 0, whereas for the unscreened case, we have that the charges gently go to 0 while the wave vector goes to 0. This is mostly due to the effect of doping, and the important thing is that for small doping, this effect may be entirely contained in the behavior of the screening, whereas the unscreened effective charges are mostly the same as for the undoped case. But this is not always the case. When the doping increases and we get to a metallic situation, the unscreened effective charges have a very strong dependence on the doping level, even in the static case. So from the study of effective charges, we can also study the impact on the observables, for example, on the well-known effects on the LEO-TO splitting, in the textbook LEO-TO splitting. In order to do so, we have to rewrite the dynamical matrix and the electron phonon coupling in a way in which they are proportional explicitly to the electric matrix, in particular to the electronic part of the electric matrix. With a bit of math and a bit of complications, one can reduce the formula for the long-range part of the dynamical matrix and of the electron phonon coupling as a function of effective charges alone. Therefore, we can say that the effective charges are the quantity that lead the physics of effects such as the Fröhlich coupling and the LEO-TO splitting. For the undoped case, this is naturally known. For the doped case, this is an extension For example, we can see from the effects on the frequency of the electron-phonon coupling, which follow from the behavior of the effective charges. And in particular, we can see that the LEO splitting, which is tending to a constant in the undoped case, gently go to 0 in the case of adopted semiconductors. And the same can be seen for the Froelich coupling, which should be divergent in 3D material in the undoped case, whereas it goes to 0 in the case of the presence of doping. We have studied this both via ab-initio calculations and also via Wannier interpolation, and even in this case, we ended up with the conclusion that the effect of screening are mostly determined by the electron screening function in the weak doping regime, whereas in the strong doping regime, also the value of the effective charges change. In particular, this is important because the effect on the observables may be seen, for example, on the line width of electron. We can plot the line width of the electrons as a dashed region around the electronic dispersion. In the case in which we do not consider the effect of free carriers, the presence of free carriers in the material and use state-of-the-art methods for the undoped semiconductors, and we can plot the same thing where we introduce the effect of free carriers, and we can see that the line widths are strongly different. Of course, this is not the whole story because one should include dynamical effects in the screening, but this was just to show that we can extend the concept of effective charges in the static case to the presence of free carriers, and they may display an important dependence on free carriers presence. Now, for the second part of the talk, let's move to the realm of frequency dependence. So up to now, we just studied only static charges, and again, I stress that we showed that we can we can deduce and compute well-defined unscreened effective charges even in presence of doping and in presence of free carriers also as in a metal. And we can study in this case, for example, the reflectivity spectrum of materials which are of technological interest. In this case, we can plot the reflectivity spectrum of H3S, in which if we just use the Drude model, simple Drude model, we have a sharp drop at the plasma frequency, whereas in general, if we consider the effect of scattering, we have a reduction of the reflectivity from 1 to a value which is not very distant from 1, but is distant enough in order to let some additional peaks to appear, which are the peaks that we are interested in because they reveal the presence of vibration in the system. In this case, the reflectivity is written as a function of the electric function at q equals 0, so is a function of omega. And our interest is very dragged towards the study of bad reflecting metals, which are the ones in which the reflectivity is not perfectly 1. One of these cases are bad metals where there is a strong level of interactions. Now, as anticipated before, for the epsilon to the -1, also for the epsilon, we can perform a separation of the degrees of freedom in which we can isolate the contribution of the vibrations to the dielectric tensor. In particular, we have a dependence on quantities that are called oscillator strengths, and which depend on unscreened effective charges that are the one that were the main subject of the previous talk, in which these quantities may be seen as dynamical effective charges, which may be expressed as a bubble in which one vertex is a velocity, the other vertex is electron-phonon coupling, and then we have the electronic bubble. As shown before, these are well-defined quantities for metals. And now we found ourselves, though, with two definitions of unscreened effective charges. One which follows from the static theory, and one which follows from the dynamical theory. Now, the big question is which one shall we use in order to reproduce experimental data and in order to, for example, reproduce the data of infrared absorption. Actually, we should use both. In fact, let me introduce some physical scales and some which are the frequency, the momentum, the line width, and the typical interband frequencies which regards interband transition. And let's consider, for example, the response due to the electronic bubble and then therefore to the electric screening, which appears here in the bubble of, so basically it's the F minus F part of the formula. So in this case, we can have, in this plot, in the frequency momentum plot, we have some regions which are related to intraband transition and some regions which are related to interband transition. In particular, this is the electron hole continuum, which is typical of, for example, so a Lindard model. And let's consider two mathematical limits, which are the dynamic and the static limit. The static limit is defined as the one in which the frequency is sent to 0 before the momentum, and the dynamic one is the one with the reverse order. In particular, let's consider them in the clean regime. It is in the regime where the line width is 0. So these two regimes are the regimes where we actually can do calculation, because in the FET we are in this regime. We are in the clean regime. So we have these two limits at end that define the two kind of effective charges, the static and the dynamical one. We know that for basically the response, from the theory of the response, these two limits do not commute in the clean regime. And the reason is that there is the arisal of an intraband term, which can be cured, this discontinuity, as soon as we introduce a bit of dirtiness in the system. And with dirtiness, I mean the fact that the line width is different from 0. Another, the opposite of this regime is the one where we have an ultra-dirty regime, where the line width is very much larger than the frequency, but we keep it still less than the typical interband transition energy. In this case, the static and dynamical limits commute. And in this case, as discussed a bit in the question session of the previous talk, in this limit, the evolution is so slow that the system is practically considered to be evolving adiabatically. So in this sense, what we can say is that we have a mathematical description of quantities, which is, we can assess the mathematical description of the dynamical limit in the clean limit, with which we can define and compute the dynamical effective charges. And these limits correspond exactly to the physical dynamical limit. Instead, the mathematical description, the mathematical limit in which we can compute the static effective charges, which is the clean limit in the static regime, it corresponds to the physical case where we have the system is very dirty. It's a bad metal, and the line width is very large. A confirmation of this physical argument may be found in the extended Drude model, in which one can express the effective charge at a generic frequency, at a generic line width, as the sum of the dynamical effective charges plus the difference between the static and the dynamical effective charges, times a factor which depends on the ratio between the frequency and the line width. This is an intraband term which can be turned on basically by the dirtiness. We can therefore call what corresponds to the mathematical clean static calculation of a quantity the adiabatic limit in which we simulate the physical limit of ultra dirtiness. So let's see what are the consequences of this. For example, on the study of the reflectivity spectrum of H3S at 150 gigapascal at room temperature. We can compute the reflectivity through the epsilon of omega tensor with a formula shown before, introducing in it the effective charges computed in the adiabatic static or static, if you want, regime, the one in the dynamic regime, and the one that are computed in the intermediate case with this formula, this interpolating formula, inserting for the line width and the frequencies the one that can be that are deduced from a Shah calculation, a self-consistent stochastic harmonic approximation. In this case, we can see that the reflectivity spectrum of the adiabatic case in yellow and the one of the dynamical case in light blue are very different. And the reason is that static and dynamic charges may be very different. Up to their difference may be up to the order of 100%. The intermediate regime instead is in between the two, and from a qualitative point of view, it well represents the experiments that are reported here on arbitrary scale. As a last bonus slide, so before in the previous talk, we saw that there are some rules for the effective charges, in particular the dynamical one, which may be related to the plasma frequency. Also, for the calculation of adiabatic effective charges for metals, we found that there is a sum rule, which includes a kinetic term, which is dependent on the expectation value of VMP, and a term which depends on the electron-phonon coupling. Both terms depend on the derivative of the Fermi function, therefore they are strongly dependent on the Fermi surface, and this formula goes back to 0 in the case of semiconductors, which is required by charge conservation, while this is not required by charge conservation in metal, because the charge conservation would be not on the unscreened effective charges, but on the screened one. And basically, the dielectric screening kills everything and allows for charge conservation. In particular, we tested this sum rule by first computing the effective charges through the calculation of the induced density by an external perturbation, and computed the various terms of the expansion, and comparing it to the analytical formula that we found. And we found that the direct calculation and the sum rule agree within a 1% error. Therefore, we are very happy of this sanity check. And also, importantly, we did not do it only on H3S, but also, for example, on the test case of aluminum, where we find that the sum rule for the adiabatic charge is 6, around 6, whereas the one for dynamical charges that was shown in the previous talk is around 2. So, in conclusion, the message that I wanted to convey is that we can define screened and unscreened effective charges for the metallic case, or in general in presence of free carriers, even for doped semiconductors. The screened one are an important one in order to describe Hill's experiments, electron-phonon, while the unscreened one are important for infrared absorption. We can assess through the FT calculation the clean static and the dynamical regimes for the determination of the unscreened charges by direct computation. But in order to reproduce experiment, the two of them interplay in the general case, and independence of the physical limit that we want to describe, we have to choose which one to use. The second part of the talk, I'm very in-depth to Guglielmo Marchese for all the theoretical developments and the calculation, and therefore I refer to his poster in order to have more details about the matter. And finally, I leave some bibliography for interested people, and that's the conclusion of my talk, and I'm open to questions.
Questions?
Very interesting talk. So I had a question on the beginning part where you calculate the LOTO splitting. So I guess in that case, you had the static charges, so the frequency was brought to 0, and then Q was brought to 0. So the effective charges were 0 at Q equals 0. And I was just wondering, is there a situation where you would have finite LOTO splitting at Q equals 0?
Yeah, yeah. So I said that I was limited to the static case in the first part of the presentation. In general, one should consider the physics of the frequency dependence of the dielectric response. In particular, one should look in the plane where there is the presence of the plasmons, the plasma frequency, etc., etc. As a function of that, one should determine the region in which the screening is mostly static or is mostly dynamic. Now, this was done in order to show that we can still, in the limit of high dope semiconductors, where the static case prevails, we can reproduce the reduction of LOTO splitting, which is seen in some experiments, and we can still reproduce, we can still define effective charges. But of course, these effects are strongly dependent on the region of the omega Q region in which you are. And actually, we are studying it in order also to understand which are the effects of these consideration then, for example, on transport. So, yeah, it's very difficult. Yeah.
The questions? Okay, if not, in the interest of time, I think we can thank again Francesco. So can I kindly ask you to wait 1 minute for the scientific members, so scientific advisory board, to leave and not to overcome you in the queue. Thank you.
Sì, io ho messo sulla schermata.
Con una chiavetta USB?
Sì, faccio la presa.
Ah, ok, e la chiavetta ce l'hai presa?
È tipo una mia chiavetta.
Questa dove l'hai messa qua?
No, lì credo, ma dovrebbe essere un tipo che gestisce questa cosa, e poi me la porto dove la faccio.
Ah, ok, perfetto. Comunque bisogna la chiavetta, da parte. Grazie.
No, buono, magari se connesso a internet poi
tu hai due possibilità, il microfono ce l'hai wifi, cioè questo qua, questo mobile, giusto?
Sì.
E c'hai il puntatore che è questo qua.
Questo qui punta, infatti mi sono...
Punta bene?
No. No, se no uno può puntare lì.
Ah, può puntare anche lì?
Sì. Però qui...
invece quello standard, c'è il puntatore.
Poi non so. Forse è bello questo.
Vabbè.
Grazie.
Okay.
So there's nothing but Hello, everyone. So we need to start the session a few minutes before 2 o'clock. So we have we have a special thing that Michele Casula will do for remembrance, and then he will give us a talk on Monte Carlo methods. He's an expert, and we're really lucky to have him talking about the Monte Carlo methods. And in addition, he's from Trieste, so one of the very few people here who actually is from Trieste. Michele.
Okay. So thanks, Richard, for this nice introduction, and my thanks to the organizers for giving me the opportunity to present my work. The work is about structural properties and phase transitions of hydrogen and hydrogen-rich compounds using quantum Monte Carlo. So I'd like to dedicate this talk to Sandro Sorella, who sadly passed away last year. And he was inspirational for the whole condensed matter community, for our community. That's a picture of him in one of the nice Telluride meetings in Colorado. And the material I'm going to show you today for remembering him comes from Matteo Calandra as well, Giuseppe Carleo, Kosuke Nakano, and myself. So Sandro trained and built a new generation of scientists by counting the number of PhD students and postdocs. We counted 27 of them, mentored and advised by him. And the majority of them found a permanent position, either in the academia or in important companies. And those who have no position yet, maybe are too young to get one. So, and it's impressive also the widespread of his impact in terms of mentoring and building this new generation of scientists. So I've been lucky of being advised by him for my PhD thesis. This happened starting from 2001, and I remember when I met him, his way of convincing me to work with him was saying, let's do it on a lattice. and that's a typical way of talking by Sandro, using very his own jargon. It was very typical of him. And then I understood that by this "let's do on a lattice," he meant to develop a new diffusion Monte Carlo algorithm by using a lattice regularization, and that was the birth of a new method called now LRDMC. So his quest in terms of scientific research was headed towards efficiency and accuracy of the methods to solve key problems. And one of the key problems is superconductivity in strongly correlated systems. And if you like, there's a fil rouge of his career. He started working on he started working on superconductivity back in early 2000, and then he kept working on that till the last weeks of his life. And this is a paper posted to the archives, modified a few weeks after his terrible accident, where he provides the most advanced phase diagram of the two-dimensional Haber model in the interaction strength and doping. If I'd like to highlight Sandro's gems, I would pick 4 of them. The first one is the stochastic reconfiguration algorithm used to optimize wave functions. Thanks to this algorithm, he proposed several new wave function, variational wave functions to describe strong correlation. And then I'd like also to highlight his work on the algorithmic differentiation applied in quantum Monte Carlo, and finally the creation and the development of the Turbo RVB code. So I'm going to go quickly through these points. The stochastic reconfiguration has been a pioneering work written by Sandro in 1998 and inspired several other works, not only in quantum Monte Carlo, but also in machine learning. So there is a machine learning version of it called natural gradient descent, has been written contemporarily, but the link has been discovered recently. And the stochastic reconfiguration method is one of the best optimizers for any variational states, ranging from Jastrow form to neural network states. And also it's used by optimizing the parameterization of quantum circuits, as we have seen yesterday by the next talk of Thomas Ayral. His eternal quest for a better variational state is never ending, right? Because you can always imagine of a better one. Started by exploiting at most the flexibility of the resonating valence bond. He was really a fan of Anderson, and he liked the variational approach behind the RVB theory. Applied to strongly electrostatic spin systems, but not only. Then he used that same framework to compute the pairing symmetry in cuprates and iron-based superconductors by determining the symmetry of the condensates entirely from first principles in a strongly correlated framework like quantum Monte Carlo. That was a very nice work. And also, he proposed very recently a new paradigm for the chemical bond in case molecules possess local spin moments by coupling covalent bond with spin fluctuations within the Pfaffian approach. That's I see as a new paradigm for quantum chemistry. And let me mention about algorithmic differentiation. It has been he pioneered the use of algorithmic differentiation in the context of quantum Monte Carlo together with Luca Capriotti. These led to the possibility of computing ionic forces in quantum Monte Carlo with the same scaling as energy. And so this was a breakthrough and paved the way to performing QMC-driven molecular dynamics and QMC phonon calculations within a correlated framework. And finally, I'd like to mention the Turbo RVB code. So The development started 22 years ago, and it's a huge code. It's an independent package, very flexible, can be used both on open boundary conditions and periodic systems with different variation wave functions and interfaced also with its own DFT engine. And there is a list then of a family of codes which are interfaced to LoRaWB to make it easy, its usage easier. And so I'd like to remember him as someone still biking with us, and he opened for us, he paved a way thanks to his findings, thanks to his tools, and we can keep biking on this road and with many things ahead, thanks also to, particularly to his precious work. And personally, I remember him as a very honest person. He's a model for me of scientific integrity, honesty, passion. So he was extremely passionate of his work, and also was a hard worker, beside, of course, the brightness of his mind. Okay, so now let's move to this. Okay, so let's now move to the content of my talk. So that's the outline. I will start by talking about the challenges behind materials containing hydrogen. I'd like to talk about the high-pressure hydrogen phase diagram. If I have time, I'll talk also about the proton transfer in water clusters, and then I'll draw the perspectives. So quantum materials, so hydrogen and hydrogen-rich family materials belong to the family of quantum materials because both electrons and nuclei are quantum particles owing to the light mass of hydrogen, and so it's quantum delocalization. So the nuclear quantum effects lead to remarkable properties. One of these properties is the high temperature superconductivity. So H3S discovered and measured in 2015 was a record-breaking measurement in terms of critical temperature, breaking the previous record of mercury-based cuprates. And then it is followed also by other compounds like lanthanum hydride, showing even higher critical temperatures. So in this talk, I'll focus on pristine hydrogen. So hydrogen has been proposed. I'm sorry for this misalignment of the PDF. So hydrogen has been proposed by Ashcroft. That's supposed to be the paper by Ashcroft, appeared in '68, where he proposed hydrogen as a room temperature, very high temperature superconductors, because it could meet, in principle, the three golden rules of the BCS gap to maximize the BCS gap, namely a large nuclear vibration, a large electron-phonon coupling V, and possibly a high electronic density N. Now, the electronic density N is the weak point of the story because hydrogen at ambient conditions is an insulator due to its molecular nature, and it has an extremely complex phase diagram. At the age of Ashcroft, this was not known very well. And actually, the insulating region of hydrogen extends up to very high pressures. And so the idea is now to make it atomic such that you lose the insulating properties borrowed from the large HOMO-LUMO gap of the molecules. So the quest for the atomic hydrogen, metallic, has been the holy grail in high-pressure physics since many years. And still, it's a terra incognita here because due to the very high pressure now expected for this phase. Now, if you look at the phase diagram of hydrogen, the complexity can be compared to the one of other compounds like water, and they are shared by if you like, the similar situation of being quantum materials, in the sense that you have the presence of a strong interplay and competition between internal electronic degrees of freedom and the vibrational energies due to the light mass of hydrogen in both compounds. So what is the challenge here? The challenge is that as these phases, these crystalline symmetries differ by very few millielectron volt per unit, you need an extremely accurate evaluation of the electronic internal energies and also a very accurate treatment of the nuclear degrees of freedom by a quantum description. And so on the top of that, you should also be able to describe the interplay between these two ingredients. So for the electronic part, the quantum Monte Carlo method is a natural choice because you need to describe these phases over a very large range of pressure and temperature and thermodynamic conditions. So the flexibility and accuracy of diffusion Monte Carlo in particular is requested in this framework. And indeed, quantum Monte Carlo has been the method used to tackle the phase diagram of hydrogen since the beginning, and I'm happy that Richard is chairing this session because he was one of the pioneers of studying the hydrogen phase diagram using quantum Monte Carlo methods. We did it separately. Here I show one of the most advanced and well-established phase diagrams for hydrogen using quantum Monte Carlo. Both published in 2015, one by Drummond in the intermediate range pressure range, and the other by Morales and co-workers in the extreme high pressure range. In this work, I focus on four main phases. I'm just addressing the extreme high pressure range, looking for the atomization of hydrogen, possibly. So I take into account the C2C, which is the well-established phase 3, and then the three other competing phases with respect to C2C in this range, namely CMCA12, which is still molecular, CMCA4, which is again molecular, and finally the cesium-4, which is atomic. Now let's have a look at the state of the art by Morales. So you have that's the phase diagram, the enthalpy as function of pressure computed with static lattice. So the ionic geometry is fixed at the equilibrium configuration for DFT DF. On the top, you do quantum Monte Carlo, and with quantum Monte Carlo, you get this phase diagram. You see that the atomic phase is very high in pressure, above 650 gigapascal. Now, if you include the lattice dynamics at the harmonic level, you get a drastic change. First of all, the atomic phase is pushed down in pressure, and secondly, there is a point here where there are basically many phases competing. Actually, all of the three phases I mentioned before competing in a very close range in pressure, and given the accuracy of these data points, it's hard to discriminate between. It's hard telling who's the winner here in this region. So we'd like to investigate this, and by the way, at this magic crossing point in pressures, there is a transition detected experimentally. And that's detected by Lubeir very recently, 2020, where he found a drop in the optical gap signature of a phase transition. And if we look at the lower pressure side of the phase transition, we have a good agreement between the optical gap computed with quantum Monte Carlo by David Sepperly, Carlo Pierleoni, Holtzman, and Gorelov. You have a pressure dependence which follows very well the experimental data, but the higher pressure side of the phase diagram is still unclear. So we'd like to address this part here now. To address that part here better than the state of the art, we included quantum anharmonicity. So we need to go beyond the harmonic theory for the lattice dynamics due to the strong fluctuations of the hydrogen nuclei. And how we do that? So we combined the self-consistent harmonic approximation computed at the DFT belief level with very accurate internal energies computed by diffusion Monte Carlo. And we put together the SCA vibrational 0-point energy, because we are at 0 temperature here in this work, with the DMC internal energy for the final phase diagram. So I skipped the description of the self-consistent harmonic approximation given very nicely by Lorenzo Monacelli yesterday. And in terms of the quantum Monte Carlo technicalities, we used a wave function written as a product of Jastrow factor times a Slater determinant. Both factors developed on a Gaussian basis set periodized, and the Jastrow with a one-body, two-body, and many-body part to reduce the variance. So we've been very careful in doing quantum Monte Carlo in this case because we need a very accurate extrapolation to the thermodynamic limit. So we simulated sizes up to 1,024 atoms for the atomic phase and up to 7,068 atoms for the molecular phases. And this has been done systematically for any crystalline symmetries and for any pressures studied in this work. Additionally, we checked the impact of the fixed node approximation because we carried out diffusion Monte Carlo on the top of the variation wave function. So we analyzed the impact of the fixed node approximation bias by optimizing the nodes at a smaller supercell size of 96 atoms, and by correcting this bias also to the larger supercells. Okay, so that's the results we got if we compute quantum Monte Carlo on a static lattice, so on the centroids, on the deformed lattice by quantum anharmonicity provided by SCA. So it's not the equilibrium geometry of DFT, it's the equilibrium geometry including quantum anharmonicity. And so that's the phase diagram with the static lattice. Now, let's focus now on two phases: the atomic one, the cesium-4, and the referenced C2C phase 3. Okay, just to illustrate how things go in this case. So if we include harmonicity, so Bilip phonons computed at harmonic level, we have, as Morales predicted, showed already, we have a strong shift towards lower pressures of the enthalpy of the atomic phase. But now, if we include anharmonic effects using the 0-point energy coming from SCA, we have the backwards effect. So we go back in pressure again. So if we combine these together, we get this final phase diagram. And now you can see two main things. The C2C is always the phase 3 stable, but the region here where the molecular phase CMCA12 was very narrow in the previous phase diagram, now it's much wider, and the atomic phase is pushed towards much higher pressures, and we predict a transition from the molecular CMCA12 to an atomic cesium-4 at about 550 gigapascal. And now it's clear that the experiment by Lubaire measured the transition between two molecular phases, because now the atomic phase is clearly separated from the other two. And our findings rationalize several experiments, not only based on conductivity, but also optical spectra and reflectivity. So we expect a shiny sample, of course, in the atomic phase, and the shiny sample should be expected above 550 gigapascal according to our error bars, and that's in disagreement with the experiment by Diaz and Silveira, the famous one, who claimed the realization of the atomic phase of hydrogen already at 500 gigapascal. So this is a debated experiment, and we are in disagreement with this. Now, let's look at the isotope effect. So thanks to the anharmonic treatment, the quantum treatment of ions, we can also study the isotope effect. So we found a strong isotope effect in both phase transition, both molecular-molecular and molecular-atomic. Unfortunately, replacing hydrogen with deuterium doesn't improve the situation, because actually it worsens the situation, because the atomic hydrogen is pushed at even larger pressures, okay? On the other hand, we can check actually the isotope effect measured by Lubaire very recently in 2022. So he found an isotope effect at the transition between C2C and CMC12. And that isotope effect of 35 gigapascal agrees very well with ours. And as Lorenzo pointed out yesterday, so these works are completely independent, so we were not aware of Lubaire's work, and we've been happy to see that there was, and this kind of agreement which somehow supports the interpretation of this phase transition as a phase transition between two molecular phases. Okay, so that's a hydrogen wrap-up. So I showed that that we've been able to combine quantum Monte Carlo with SCA. I showed that the importance of an harmonic contribution to describe correctly the hydrogen phase diagram. So we predict a very high pressure for the atomic phase to be stable. And we found a large isotope effects in both transitions, and the one by Lubaire associated with the direct gap closure is a molecular to molecular phase transition. Okay, so now let's move forward. How I'm doing with the weather? With the time? Okay. How long? Okay, 6, okay, I try to accelerate even more. So, okay, so the second part of the talk is about proton symmetrization. Proton symmetrization is another process where you need a very accurate determination of internal energies, and also an accurate description of quantumness for nuclei. So it's shared by many compounds. It's present in H3S, the sulfur hydride we mentioned before, in water ice as well for the ice-7, ice-10 phase transition. But we'd like in this work, we'd like to focus on a different system, on a water cluster, on a protonated water cluster, and also in these kind of clusters you have the physics of proton symmetrization. So why protonated water clusters are interesting? Because the additional proton, the charge effect, is sort of a probe to study proton hopping and hydrogen bond strength. And you have usually in this cluster two limiting species. You have a shared proton, a symmetrized proton in the Zundel species here on the right-hand side, and you have a localized asymmetric, if you like, configuration where now you form an hydronium in the middle, and with a solvation shell giving rise to the Eigen species. So these two, Eigen and Zundel, are known to be the limiting species of proton hopping mechanism in water and water clusters as well. So we started building the Zundel cation plus the solvation shell around it, such that we get a protonated water hexamer. So now we have 6 water molecules surrounding the charge effect, the proton in the middle. And this protonated water hexamer is the smallest cluster, including both limits, the Zundel-like, the symmetric one, and the Eigen-like, the asymmetric localized one, in a same cluster. If you plot this sort of phase diagram for the cluster, you have the Zundel-like configurations when the size of the core is small at a short water-water distance. And at a large water-water distance, you are in the localized eigenlike situation. The bar, if you are in the localized limit, you have, of course, a barrier for the proton to hop to one molecule to the flanking molecule, and the barrier is very small, and that's a list of values according to the methods for two distances plotted as a vertical line here, solid line. So you see that the values in Kelvin are close to room temperature. So it means that not only quantum effects are important, not only you need to have an extremely accurate resolution of the energetics, but also you need to include thermal effects, okay? And so in this work, what we did, we combined variational quantum Monte Carlo for the electronic part with a thermal bath provided by Langevin dynamics, and we propagate the equation of motion for nuclei using a path integral scheme, path integral Langevin dynamics, with an algorithm which is very efficient, has been developed earlier by some of us, and it's called in this way, but so it's a way to integrate this very efficiently. And we need this to be able to perform these calculations, which are very challenging. So we've been able to run 40 picoseconds of dynamics using quantum Monte Carlo forces. So if you look at the core size here, we can now study the oxygen distribution function of the core, of the Zundel core of the cluster, and we can now study the thermal expansion of the core size as a function of temperature, of course, and we see the results of both classical and quantum simulations. And in the quantum case, we have a very, very small thermal expansion. I mean, almost negligible up to room temperature, and then we have a shoulder here. So it means that quantum effects make the hydrogen bond robust in temperature. That's the first observation, which is very important. And the second, I don't know why it is, tilted. We study the proton hopping through the distribution of instantons. Okay, so we take an alternative approach. We'd like to study the dynamics of the hopping of the proton by studying the statistics of instanton events. So the instanton events are those events where the polymer describing the quantum proton in the middle is equally shared by the left-hand side and the right-hand side of the phase space. Is equally shared by the left-hand molecule and the right-hand molecule, water molecule. Yes. So now, sorry for that. I don't know why. So then we can do a study of the distribution. We can compute the cumulative distribution as a function of the distance, and okay. So that's. Let's see if it's, okay, so this is fine. So by studying the cumulative distribution of the instanton statistics, we'll be able to find that there is a sweet spot for proton transfer around room temperature. So from 250 and 300 Kelvin, there is a sweet spot. And the sweet spot is explained by the increase of short Zundel events. So this peak here is driven by, if you resolve the peak in terms of contributions coming from different configurations, it's an increase of short Zundel events whose peak happens the same temperature range. So this is sort of surprising because short Zundel events are events which is classically have a high energy because they are belonging to the repulsive part of the potential. So we'd like to understand this, why the short Zundel events are so important, so relevant here, despite being a higher energy in the classical framework. And so we tried to basically derive a model, a potential energy model, involving the two relevant degrees of freedom, the shuttling mode and oxygen-oxygen vibration mode. And by quantizing the shuttling mode, okay, so this basically is a reduction in dimensionality from the full quantum Monte Carlo driven MD. So by studying this potential and by quantizing the shuttling mode, we discovered that the 0-point energy of the shuttling mode, which is also tilted, I don't know why, so it's a PowerPoint version, which is not the same as mine. So you have a larger 0-point energy on the eigen side and a lower on the short Zundel side. And so this basically penalizes eigen-like configurations and sort of favor, and in contrast, Zundel-like configurations. And so let me wrap up about this water axiomer. So we found this importance of 0-point energy to balance between eigen-like and short Zundel-like instances. This explains, because the potential now, the effective potential now is harmonic, is remarkably harmonic. This explains the very low thermal conductivity found in the Zundel core. And also, it suggests that indeed short Zundel configurations are relevant to this optimal sweet spot for proton hopping due to the interplay between temperature and 0-point energy. And so let me just say the last word. The combination of quantum Monte Carlo plus methods, including quantum nuclear effects, is at infancy, if I can say so, because we need, if you like, to improve efficiency to tackle larger systems. And one of the ways to do this is using machine learning techniques to derive effective force field potentials by keeping the quantum Monte Carlo accuracy. And that's a work in progress. And you see a lot of papers now exploiting quantum Monte Carlo data sets to derive machine learning potentials. And with that, I thank you for your attention, and I take your questions.
Thank you. Okay, everyone. Thanks for the really nice talk on this beautiful methods. And we have just a very short time, but please, somebody ask a question. Yes, there's one. Sandro.
Thank you, Michele. Very nice talk. One of the additional interesting properties of hydrogen that actually Neil Ashcroft pointed out in his paper is the fact that the vibrational energies have the same scale as the electronic excitations. You show this figure from experiments showing that the energy gap is 0.5 electron volts, which is exactly the vibrational energy. Yes. So, of course, the question is, what about the Born-Oppenheimer approximation?
Right, yes, indeed. Yeah, that's another challenge. Of course, everything here is within the Born-Oppenheimer approximation in the study adiabatic. So, yes. The solution to that is to write down, a collective wave function including both nuclear and electronic degrees of freedom in a quantum Monte Carlo framework at the wave function level, for instance, and this will include naturally also non-adiabatic effects between the two components. So at the end, you're gonna aiming at writing down a two components wave function. Okay, so this includes an additional complication. At the variation level, maybe it's possible, and I think there's some groups working on that. But that's the way to go, to write down a two-component wave function.
Okay, so we have time for one more question. Well, I'll ask it. Is a sweet spot something that's really interesting about room temperature and the proton?
So we know that proton transfer is sort of important also for everyday life, for the biological processes, because water solvation is necessary in different biological situations, for protein folding and so on and so forth. So the fact that the efficiency of the proton transfer is maximized in a range close to room temperature is fascinating. it's a fascinating perspective, and I was surprised when I saw this data, and so I think it's an interesting point.
Hope you're discovering something interesting. So we must thank Michele again. And the next speaker. Here you go. You're getting ready. I'll pull out my...
I give you my mic.
Schedule, I hope. Please, then, correct me, from the Perimeter Institute. I don't have it.
Oh yeah, hopefully it's not going to die to me.
Okay, 25 minutes plus 5.
Oh, okay.
Okay.
Slides.
Okay, we'll have this working soon. Here comes help.
I did this.
Unmuted, okay.
Thank you. The audio. See if,
Hello, can you hear me? Yeah. Sweet. And what's the pointer? How does it work?
Sorry?
It doesn't work.
It works, as you can see.
I can do.
With the mouse.
Okay.
Okay, and back and forth.
Okay, thanks.
okay, go ahead, please.
Thank you very much. First of all, I would like to thank the organizers for the opportunity to present my work. I take the opportunity to thank ICTP as well. I am a product of ICTP. I feel like I'm home here. I did my diploma program here. I did my PhD between ICTP and CISA. So I'm like very, honored to be here in front of my professors and give this talk. So as you can see in the slide, I'm a research scientist at the Perimeter Institute. I have affiliation at the University of Waterloo. I'm also co-founder and CTO of my own startup. So how do I stay in the quantum superposition of doing academic and entrepreneurial work? I will tell you in a minute. So I am lately very much interested in solving optimization problems, but I'm interested in solving optimization problems using some of the techniques that you guys are developing here. So quantum-inspired techniques together with machine learning. So optimization problems actually occur in a wide variety of areas. We have the so-called traveling salesman problem, which is a problem of finding the shortest path for a traveler going to a certain number of city ones. You have a problem of interacting atoms that interact via some potential. You want to basically find the configuration that minimizes that system. You have the problem of training a neural network. Nowadays, people are training binary neural network because they want to save the energy that takes into training deep learning model. You have protein folding problem, the problem of finding the native state of a protein coming from an unfolded state. And you have portfolio optimization problem, which is a problem of finding the best way of investing in the different assets that you have in your portfolio, which one of my students is actually working on with Quantum Monte Carlo. And you have many more problems.
So why are all of these problems interesting for me as a physicist? It's because they could be cast in the form that I understand, which is the form of an Hamiltonian, basically. And solving them with whatever constraints that your problem has is equivalent in simply minimizing that Hamiltonian, or finding the ground state if you want, right? So we can typically use all of the methods that we've developed over the decades to basically find ground state properties of classical or quantum systems to be able to solve all of these optimization problems. But there's a problem. Some of them are very hard to solve. Like, for example, the disorderizing glass in the random longitudinal field, find the ground state among 2 to the n possible states n we have, right? So typically what people do, depending on the application that you're interested in, you kind of relax your initial assumption of wanting to find the lowest configuration. Near optimal solutions are okay. So basically people develop heuristics methods that find near optimal solutions. One of the most popular methods, so another thing that I like to see is like visualizing my optimization problem as some sort of very crazy landscape that has a lot of local minima, a lot of saddle points, and then solving the optimization problem is finding the deepest value in that landscape, or finding a near optimal value, basically. So one very popular method is basically exploring that landscape using thermally or fictitious thermally activated processes, right? And this has been inspired by a method in metallurgy whereby you basically, to make a material more durable, you kind of heat it up at a very high temperature so that it can explore high energy state, and you slowly cool it down so that the atoms rearrange themselves in configuration that minimizes their free energy, right? And so this is the so-called simulated annealing method that was invented in IBM Watson to basically optimize chip design. Another paradigm is basically to, instead of using thermally activated processes, you can use quantum tunneling to basically explore your landscape. And so you have the so-called quantum annealing method, which aims at finding the ground state or the global minimum using quantum tunneling. And that has been also implemented on some dedicated hardware. Here I'm mentioning 2 of them because they are actually available on the cloud, and you can simulate quantum annealing with them. All right? So basically, this is the paradigm of either searching for the ground state, either using thermally activated process or quantum activated process. Which one is better? But we don't know. I mean, usually it's like heuristic, it's kind of trial and error. But in a lot of applications, people have found quantum search to be better than a classical search. But what I would like to highlight is that most of the techniques that have been used, either to benchmark the quantumness of some of the devices that we are building, or to see whether there's any kind of quantum advantage in using them, is by actually simulating the dynamics of either simulated annealing or quantum annealing on my laptop or whatever HPC architecture. All right? And what people have been doing, have been using to do that is using Monte Carlo methods, either classical Monte Carlo methods for this emulation of simulated annealing, or using quantum Monte Carlo method for the emulation of quantum annealing. So probably you recognize a lot of those methods here, and those methods were not designed to solve optimization problems, right? They were designed to basically find, like the previous talk, equilibrium properties of either classical or quantum system, right? But here they were repurposed in order to solve optimization problems. So we're inspired by that, and by very recent work that we're actually using neural network to simulate equilibrium properties of either classical system or quantum system, and then we ask ourselves whether we could repurpose them as well to basically solve optimization problem in an annealing paradigm. So next I will give a very brief introduction to variational Monte Carlo, which is one of the bedrock methods that we use to emulate annealing. And VMC is basically the quantum Monte Carlo method that is used to find ground state properties of quantum system at 0 temperature. It does that by simply minimizing the so-called variational energy, expectation value of your quantum Hamiltonian over your variational state. So by definition, your variational energy is an upper bound to the true ground state energy. So you just have to minimize it to optimize the parameters. So I would like to point out to the talk by yesterday, because in principle, that answer could be whatever. Yesterday we had a quantum circuit whereby basically you do variational quantum eigensolver to be able to represent the quantum state with a quantum circuit. Here we use actual neural networks. And then we have a typical thing. You replace quantum mechanical expectation value with statistical ones, and then you optimize the answer just taking the gradient and taking whatever flavor of the optimizer, stochastic gradient descent, momentum, stochastic reconfiguration. Here I would like also to give a tribute to Sandro, who is like you saw in the previous talk, he was really a leader in basically designing ansatz for variational Monte Carlo, especially stochastic reconfiguration techniques that nowadays is like state of art as well to basically optimize neural network. All right, so next, which ansatz do we choose? So we actually choose neural language models, and I will tell you in a minute why. Neural language models are very powerful probabilistic models that are used to find correlation between words in a language. So basically, when it has learned that correlation is able to predict the next words given previous work. And I believe that all of us are using that when we write emails nowadays, right? So I'm going to give you a very vanilla idea of how it works with one autoregressive model called recurrent neural networks. All right, so imagine you're writing your email and then you put the input of people you're writing to with the subject. So basically, what the neural network does is that it predicts the next word. It has learned the conditional probability distribution of predicting the next word. It takes that word that it has sampled to predict the next word, and so on and so forth. So you can immediately say that if you take the product of those conditional probability distribution, you've learned the joint probability distribution of sampling the first words in your sentence, giving the input. But why am I interested? I mean, we are physicists. Why do we sample words? So the point is that this kind of autoregressive sampling could be applied to instead sample a spin configuration or a qubit. Right. And you can literally sample a qubit or a spin at a time using the same autoregressive process. And why is this interesting? Maybe I give a little bit more detail. So basically, you use the chain rule of probability distribution to be able to sample or to learn the joint probability distribution of sampling a spin configuration. And what we are actually learning with the RNN here is the conditional probability distribution that we parameterize with some parameters, lambdas, that are literally the weights and the biases that lives inside your RNN cell, right? And then once you have the probability distribution, we use a so-called softmax layer in the case that make the probability distribution by construction normalized. And that's going to be pretty important in a couple of slides. And we can represent the wave function just taking the square root of that probability distribution. Right. So one of the reasons why we use autoregressive neural networks, there are other networks that have been used, things like rested Boltzmann machine, convolutional neural networks. But the point is that if you use that network to basically represent a quantum many-body wave function, you need to figure out a way to sample, right? Because here we use an approach that is similar to reinforcement learning. We don't have a data set that we are training on. You generate the data that you train on the fly, right? And imagine that you are basically trying to minimize a spin glass, and you want to generate samples with Monte Carlo. Autocorrelation times are going to kill you, right? So we want to have a smarter way than just building Markov chains to sample. Here we don't have any Markov chains, so we have no autocorrelation times. Practically speaking, it's directly parseable, and yeah, it's normalized to unity. But as a catch, you can tell me that quantum mechanics is quantum, why do you have square root of probabilities? Well, you can also represent complex wave function with that, and we can simply parameterize the phase, let's say, of your wave function using basically still your RNN, but putting it through another layer. All right? And you do the same thing, minimize the variational energy. So now I will tell you about the RNN architectures that we use. In most of the local Hamiltonians that we are looking at, we use the tensorized RNN cell. And we saw that compared to a binary RNN cell, where basically you have your so-called hidden state that encodes the correlations, that learns the correlation between the spins in your lattice, it interacts with the local Hilbert space just through your activation function F. But we chose a tensorized version because it was a more compact representation. And when we run simulations, on the quantum Ising chain at criticality, we look at the variance of the variational energy with respect to the training step. You can directly see that the tensorized RNN converges faster at a low accuracy. So just as a reminder, variational Monte Carlo has this very nice zero variance property. So, I mean, the lower it is, the more accurate your answer is to the ground state. All right? Another thing that we noticed is that when we had disorder in the system, instead of having the same, what we call weight sharing, that is at every lattice side, we use exactly the same weights and biases of the RNN. When we have different weights and biases, which is what we call not weight sharing, there's a dramatic improvement or a dramatic difference in the ability to represent basically the wave function. And here you see that basically it's almost like 2 orders of magnitude more accuracy when we use non-weight sharing. So somehow, the RNN has to see the underlying macroscopic details of your Hamiltonian to be able to represent it well. And when we look at other isinglasses, the so-called Sherrington-Kilpatrick, which is an all-to-all interacting model with random interactions. And we found that using a different kind of RNN architecture, the so-called dilated RNN cell that uses the so-called skip connection. We saw one yesterday. And it was introduced, skip connections were introduced in machine learning to deal with the problem of vanishing gradients. Here we saw that it was pretty efficient to be able to capture the long-range correlation that we have in the Sherrington-Kilpatrick. And again, when you see the variance of the variational free energy, which I will define in a minute, you see that you can have up to 1 order of magnitude of accuracy using this kind of skip connections. So one thing I would like to highlight also, because what we did in the previous RNN cells were like more of trial and error, and usually we don't want that. But the smart way of going usually is implementing symmetries in the RNN architecture. So here in the first panel on the top left, I'm showing some results obtained by some people in my group where they basically simulate the XY model in 1D, and they show the RNN when they encoded symmetry, the U1 symmetry, and when they didn't encode the U1 symmetry, and we saw that with symmetry you converge faster. And there's another result on the J1, J2 model in 1D, where they show that when they encoded the Marshall sign in the wave function, they basically have orders of magnitude more accuracy. So encoding symmetries is important, and basically on the other panel, what they showed is basically when they plot on random direction the loss landscape where the training is obtained. In this case, it's basically the negative Loic likelihood. So the left data they actually do unsupervised learning, where they train from data they obtain probably from DMRG or Quantum Monte Carlo, and they show that basically when you don't have symmetry, it takes time for you to find the global minimum, but when you have symmetry, it's directly converge very, very fast. So yes, so we know that neural networks are universal approximators, but if you don't encode symmetry, it takes more or less forever, and it's not super accurate when you want to train it. So it's a good thing to implement symmetries. So another thing that I would like to mention, since my talk is not too much of electronic structure, I want to make sure this very nice review that was put on iCarve recently, where they discuss about different neural network architectures for fermions, basically, both in the first quantized regime and in the second quantized regime. So please have a look. Maybe it's the only thing you take from my talk. All right, so next I'm going to talk about variational quantum annealing. How many minutes do I have? 10 minutes, good. Sweet, all right. So I motivated my talk by saying that you could basically solve an optimization problem with maybe a quantum annealer by using quantum fluctuations, by using quantum fluctuation as a search of basically this kind of configuration landscape. But you could view it in a different way. You could view it in the spirit of adiabatic quantum computation. So the way we actually view it in a variational quantum annealing is that when we have an RNN, typically you initialize it with random weights and biases, right? So when you initialize it with random weights and biases, so quantum annealing, you could see it as an interpolating method, right? I have an Hamiltonian that is easy to prepare. I can easily find the ground state, but I want the ground state of an Hamiltonian that I don't know. It's hard to prepare. So I can slowly or adiabatically interpolate between an Hamiltonian that is easy to prepare to the Hamiltonian that is hard to prepare. That's kind of the idea of adiabatic quantum annealing, and you need to do it slow. So we kind of use the same ideas here. There's this Hamiltonian where all the spins point in the x direction. That's easy to prepare. The way we do it, we simply do gradient descent steps, and we land on the energy of that Hamiltonian that is easy to prepare. Next, we change the Hamiltonian. We introduce basically a problem Hamiltonian that is in glass. And what happens is that basically we shoot out of the instantaneous ground state. And we need to perform some gradient descent steps to fall back on it. We reduce again the quantum fluctuations. We shoot out of the external ground state, we perform gradient descent steps to fall back on it. And so on and so forth. By the time you have completely reduced all the quantum fluctuations in your system, hopefully, we should find ourselves in the ground state of your isinglass in that case. So we came up with a theorem that we induce, a variational adiabatic theorem that tells us the number of gradient descent steps we need to perform to remain adiabatic. And its scale is bounded with the minimum gap, and the minimum gap square that you have during the annealing. And somehow, in that sense, we still have the complexity of, say, you pass through first order phase transition, exponential scaling gap, you still have an exponential kind of scaling. So there's literally no free lunch. So recap, we use variational Monte Carlo with a time-dependent Hamiltonian to be able to emulate quantum annealing. The classical formulation is pretty easy. You just have a variational free energy that we also minimize because it's also an upper bound to the true free energy. Right, and for the variational classical annealing, you also use a time-dependent schedule. And one thing that is also important is that you need to be able to represent exactly the von Neumann entropy. So if I have an RBM that is not normalized, or a computational neural network that is not normalized, I cannot basically represent the entropy, right? Because, I simply cannot. Whereas when you have a probabilistic model that is normalized, it's very easy and it's computationally efficient to represent or to compute the von Neumann entropy. So now we present the results. So here you have variational annealing on random Ising chain. We have an Hamiltonian with spins that interact with different kind of random interaction on the chain. We know what the ground state is. So we monitor the residual energy, the difference between the Hamiltonian we obtained at the end of the annealing and the exact one. We try different system size. Something I forgot to mention is that the difference that we found between an Hamiltonian-based approach where we minimize the Hamiltonian or an unsupervised learning-based approach where you are training on data. Usually when you are training on data using a negative log, like you need a lot of data to be able to learn the probability distribution. But for us, we don't need a lot of data. We usually use like 50 samples to train, which is very impressive. But once we've trained, we can generate an arbitrary number of samples. So at the end of training, we generate 1 million samples, basically. And we can do it very, very quickly, very fast. And we do averages over also 25 random realization of the disorder. So here we see that basically as we increase the annealing steps, which means that we become more adiabatic than doing some sort of quenching, indeed the residual energy is going down. Something that was surprising to us is that actually here the classical emulation of annealing with neural networks is superior to the quantum emulation and annealing. And there were previous results showing the contrary. That is, emulating annealing with Metropolis Monte Carlo with the quantum case was actually superior. So we have kind of a reverse here with this kind of variation annealing. We suspect that maybe it's the use of the explicit use of the entropic term that brings that advantage. And another thing that is also interesting, in that paper, they actually did a time evolution of quantum annealing of what a coherent quantum annealer should have. And on this random Ising chain, it has a logarithmic scaling, whereas we have a polynomial scaling. So which means that our algorithm for this system size will beat the quantum computer, which was pretty cool to see. And then we increased the complexity. We went to the two-dimensional Anderson spin glass. And again, we had to change the neural network. And a neural network, the autoregressive sampling takes into account basically the locality of the 2D Ising glass here. So we do this kind of sampling in 2D. So one thing that is interesting, again, we saw that VCA was superior to VQA. But another thing that makes us, we wanted to check that actually annealing is helping in the simulation. So what we did, we directly optimized the problem Hamiltonian without any annealing. That's the red data point. We respect the number of gradient descent steps. We see that with a large training steps, we basically lower the residual energy, but it's orders of magnitude higher than the variational quantum annealing and variational classical annealing, which means that somehow having an idea of annealing in the simulation is helpful, right? So based on that, we knew that there were previous results by Santoro and collaborators on the same model, but doing an emulation of annealing using Markov chain Monte Carlo, and we did the comparison, and it was amazing. So we saw that for long annealing time, we could have up to 3 orders of magnitude more accuracy using a variational classical annealing compared to both simulated annealing and simulated quantum annealing implemented with particular Monte Carlo, right? And this was on 1600 spin chain. We tried also a Sheraton-Kilpatrick model. Here we saw also some advantage. It was not super drastic. And we saw that most of the time, the Markov chain-based annealing techniques got stuck in local minima, and we also look at the probability of success of the different instances. And VNA or VQA in this case was almost all to 1. When you find the solution, it's almost with perfect accuracy. We even look at, basically we did PCA on the solutions that the configuration we obtained at the end of the annealing, and it was cool to see that we could even sample the degenerate ground state here in SK. So next, we wanted to tackle another problem. Like, there was this paper discussing the fact that, as I mentioned, there is basically a time scaling in being able to solve an optimization with quantum annealing, and that's the gap, the inverse of the gap squared, right? And for problems where basically you pass through a first order phase transition, you have an exponential scaling gap, which means you need an exponential amount of time. But then there was this very nice paper by Nishimori and his collaborator showing that actually you could enlarge the phase space, and by enlarging the phase space, you could find paths that avoid the first order phase transition and you pass through a second order phase transition. So you have a polynomial scaling gap. And because of that, you will have an exponential enhancement in solving quantum annealing. So here was the abstract of his talk, and he said that's the definition of non-stochasticity, by the way. A non-stochastic Hamiltonian is an Hamiltonian in which you have your off-diagonalized terms that could be positive and negative. So it makes Kernel Monte Carlo, traditional Kernel Monte Carlo, to be not simulatable because of the sign problem. The variance of the sign grows exponentially with system size. But VMC does not intrinsically have the sign problem, as I mentioned. So we asked ourselves whether we could simulate this variationally with variational quantum algorithms, and whether we could actually see the advantage by passing through second order phase transition. So we look at this P-spin model, the HP, which is basically a mean field model with range of interaction P, and the range of interaction dictates somehow the phase transition, right? The red lines here are lines where we have first order phase transition, and the blue lines are the lines with second order phase transition, all right? And we look, for example, as proof of principle for P equals to 5. So if we decide to have an annealing schedule where we pass to the second order phase transition, we just check that indeed we could simulate the dynamics, right? With variational quantum annealing, we pass to the first order phase transition, we can also do the same thing here. Next, we scale the system and we look at the success probability when we take a route passing to the first order phase transition and when we take a route passing to the second order phase transition. And we see that there starts to be a shift as we increase the number of spins in our systems. And when we look at basically the number of annealing steps that we need to have a 99% success probability, we see that it's way much more favorable passing to the second order phase transition compared to passing to the first order phase transition. One thing that was quite surprising for us is that we didn't see any exponential. We would have expected to see the number of gradient descent steps to be exponential in or the number of annealing steps to be exponential in the system size, but maybe it's because the system sizes are not large enough. But at least we can see that the route by which you pass indeed has an effect. So we check another system, the so-called Newman-Moore model. Okay, I will go through very fast. Newman-Moore model is a model that basically doesn't have an explicit disorder, but it exhibits glassy dynamics as signature of first-order phase transition. You have fractals excitation that makes it impossible to simulate with low temperature with Monte Carlo. We tried variational quantum annealing and variational classical annealing, and we saw that basically annealing dynamics was totally unstable. And yeah, so it was totally chaotic. And we're asking ourselves, why is it chaotic? We brought again a method from machine learning where they basically try to understand why a neural network without skip connection was worse than the one with skip connection by visualizing the loss landscape of the prime. And we basically did the same. We visualized the loss landscape during variational classical annealing. And we saw that indeed you have the characteristic minimum in the beginning of annealing, which is what we are supposed to be. But then it becomes totally chaotic at the end. So that's the reason why it's not efficient for that. So there's basically no free lunch. There looks to be, for some problem, there's a conservation of computational complexity. And with this, these are my conclusions. Annealing search in the variational landscape seems to outperform the search in the configurational landscape. We saw VCA more efficient than VQA and SA and SQA, but we say that we advocate that they are good candidates to solve real-world optimization problems. VQA is also a good candidate to benchmark quantum annealers with non-stochastic Hamiltonians, and we should not just look at representativity or expressivity when we use neural network ansatz for variational Monte Carlo, but also we look at trainability issues, and visualizing the landscape may help us to design better ansatz. With that, I will thank you, thank my collaborators, and I will be happy to take any questions you have.
Thank you. Do we have some questions? Questions? Yes.
Maybe I missed the point. Many of these Hamiltonian are fully degenerate in the ground state. So for example, when you do from the adiabatic, when you were doing the adiabatic connection, the Hamiltonian with only the spin interaction can have, for example, if J is uniform, this can have whatever solution you. So there is a way to select a specific ground state, or how you solve the potential fact that your Hamiltonian has many ground states in your search?
Yes, so basically if your machine learning model is able to capture the multimodal distribution of your ground states, then in principle with autoregressive sampling, you can sample all of them, right? So there's a part that I skipped very quickly for the Newman model, where basically I showed that here we have 4 degenerate ground states, and at the end of the annealing, when I generate, let's say, 100,000 samples, and I basically plot an histogram, and I see that I find all of the 4 ground states. This is when I don't have mode collapse. But if I have mode collapse, I probably collapse to one of the ground states. And maybe if you have a penalizing term in the loss function, you might bring a bias to one ground state than another. For example, you can break the Z2 symmetry by adding a longitudinal field to make sure that you go in one ground state or the other one. Yes.
Very nice talk, thank you. And I'm curious about, have you tried the real model? I see you have some model only include the Heisenberg interactions. Have you tried to like a real model, like include a very long range interactions, like Heisenberg interactions? You calculate more than 20 nearest neighbors, like include Dirac-Skimiria interactions and other interactions. So you will have a very complex system. Have you tried this?
I mean, I showed result on Sheraton-Kilpatrick is all-to-all, right?
I'm sorry?
So the Sheraton-Kilpatrick model?
Yes. I mean your quantum annealing models to find the ground state. What do you use as spin glass? I know it is very famous model, but have you tried to use a DFT calculated model, a real system, a real material? For example, you have a system that you have JS, your Heisenberg interactions, you calculate to like more than 20 nearest neighbor, and you also include Dirac-Skimiria interactions, and it will be a very huge interaction matrix. Have you tried this with your method? Is that efficient?
Okay, so if I understand, you're asking whether I tried a model that has many interacting or nearest neighbor interactions. I did. I mean, I believe like the Sheraton-Kilpatrick talks to all of its other neighbors. So in that sense, it's kind of infinite dimensional somehow. Yeah, so basically these are the results here for the Sheraton-Kilpatrick model, right? We can talk later. Maybe I don't understand the question.
Okay. Anything else? Any other questions? Not over there? Well, I'm told by the organizers that we really have to be very careful now to start the next session on time, right? So first we thank our speaker again. Thank you. Back here at 3:30. So.